Good morning, all. Sir, with your permission, can we wait for some minutes because no one has joined. Only one participant has joined till now.
Okay, absolutely fine. Yes, I could see a few only. So please let me know. I am here online only,
Okay,
Amit.
sir.
So whenever you will be asking me to start, then I'll initiate. Okay.
Okay, sir.
Okay. Thanks.
Good morning, all. Sir, I think we can start. The participants are joining. Uh, so, mm,
Okay. Thank you, Sumit. Yeah.
Morning, sir. Morning, sir.
Good morning.
good morning, all. I welcome you all in the third day of AICTE sponsored ATAL FDP on the artificial intelligence and Internet of Things in the nanotechnology sensors and communication in the making of Aatmanirbhar Bharat. The first session of day 3 will be delivered by Professor Shaibal Mukherjee on nano-scale materials for smart biochemical sensors. Now I request Professor Shaibal Mukherjee to share his slides and start with the lecture.
Thank you, Sumit, for the introduction. Yeah. Please let me share my screen with you. Let me get a laser pointer. So please let me know, Sumit, if it is visible.
Yes, sir, it's visible.
Okay, so good morning to all the participants from different parts of the country, and welcome to day 3 of this ATAL sponsored FDP program. So today's session will be shifting a little bit than our yesterday session, in which we have discussed regarding the steps and methodologies that we have followed in our research group to develop crossbar memories for next generation memory devices or advanced memory applications. So today we are shifting a little towards another domain of the research activities, in which we are just developing a number of different smart biochemical sensors. So one aspect of the development of such smart sensors has been covered by Professor Mahesh Kumar on day 1 from IIT Jodhpur, when he has delivered a talk on IoT-enabled two-dimensional TMD-based sensors. So that he has been doing, and his research group has been pursuing the work at IIT Jodhpur. So in our research group also, over the last several years, we have developed a number of different sensors, primarily heavy element sensors to detect water pollution or condition or quality of water, and also toxic gas and volatile organic compound sensing. So some of those aspects we'll be covering today in this particular session of nanoscale materials for smart biochemical sensors. So as I always do, like, since I'm presenting the work of my students who have pursued their doctoral or master's or BTech project works under my supervision. So thanks to their work only, which I'm going to, or some of this work I'm going to present in front of all of you. And as always, as also followed in day 2 of this FDP program, today also in the afternoon session, we have dedicated a session for the tutorial and the virtual hands-on training on how we are actually manufacturing these smart sensors and materials for smart sensors. So we have dedicated one complete session in today's afternoon that will be conducted by my PhD student Chandrabhan Patel. So the work which I am presenting today is been or has been initiated by Arashri, who is now assistant professor in Shibata Institute of Technology, Japan, on tenure track. And it is further carried out by Vishwajit Mandal, who is assistant professor in Center for Advanced Studies in Lucknow. And now this work has been carried out by 2 of my PhD students, Chandrabhan and Kajal. And Sujata, Shishir, and Parishmita, they have joined our research group to carry out a number of different small-scale activities in the domain of biochemical sensors. So thanks and acknowledgement to them. And also our sincere thanks and gratitude to our research funders and collaborators, because as we have mentioned over the past 2 sessions also, that due to their generous support and encouragement only, we would have been able to sustain such a vibrant research group in hybrid nano device research group at IIT Indore. And this structure of different domains of research activities, out of which the activities over non-volatile memory I have covered yesterday, and today I'm going to concentrate our work and some of our work in that sense on biochemical sensors. So in this work, again, our collaborators mostly are RMIT University from Australia and Hftm University, Japan, for the development in terms of the devices in the clean room device fabrication tools and mechanisms, since we don't have it. And also in India, we have been collaborating with CSI and CD Pilani, the group of Professor Ajay Agarwal, who has now shifted to IIT Jodhpur as a full-time professor. So some of our students are also working in close collaboration with the research group of Professor Ajay Agarwal. And Shinshu University, they are always helping us with the characterizations of heterojunctions and interface that is necessary to actually analyze the materials or what is happening at the nanoscale and the microscale at the junction of two materials in which we are trying to establish our sensors. So basically, two different types of sensors we'll be talking about. One is mostly the gas sensors, and another is the volatile organic compound sensors in today's topic. So as we all know, basically the requirement and necessity of sensor or mostly gas sensors is originated to protect human being mostly and living organisms over the earth. So the mostly toxic compound that is generated in the atmosphere from the factories or maybe the automobiles or maybe industries, those are mostly relevant to the carbon related or sulfur related or nitrogen related products. And these are extremely hazardous for various and cause various diseases in human. So that's why we need a sensor which can not only detect these polluting hazardous elements, but also they can detect at the minor concentration or the minimum concentration. In the commercial market, there are sensors available for our past several decades. Different industries have developed different commercially available sensors, but those sensors have different limitations in terms of the operating temperature. In some sensors, we do require that the temperature of operation when they are used for different applications of domestic and commercial arena, they require high temperature rather than room temperature of operations. So for that, you need to add another heating assembly whenever you are trying to couple the sensor on a portable network. So the problem or the challenges come from the operating temperature point of view. Sometimes the sensitivity of the sensor does not become too high, and that causes the problem. Even if the concentration of carbon related or maybe sulfur related or nitrogen related gases which comes out into the environment to pollute the environment, in order to detect, sometimes the commercially available sensor they require that the concentration of the analyte into the gas should be reaching at a particular level. Below that level, the sensor does not work. So the limitation comes from the detectivity or the sensitivity of the sensor. And the third, another crucial point is that whether the sensor is having extremely high values of selectivity. For example, if the sensor can detect a sulfur related product in the presence of carbon related and nitrogen related products, then it should be having high selectivity towards sulfur related analytes. But again, many commercially available sensors are having limitations in terms of reaching a particular value of selectivity if more than one number of analytes are present in the ambient. So in this line, let us see what else we are going to look for whenever a sensor is developed. So is it always related to the gas sensing application or something else also? So here the slide shows you that the sensor basically to detect various heavy elements in water such as lead, fluoride, phosphate, mercury, manganese, so on and so forth. So those are extremely crucial even if you are looking for establishing a single portable device to sense all these elements. So the water quality monitoring and to sustain the quality of the soil also that is used for the agricultural purpose, it is of quintessential importance. So farmers use pesticides, okay, during agricultural process, but it is also crucial for us to know about the byproducts of such kind of pesticides, about the amount of such toxic elements which are generated by the pesticides that is mixing with the water, and whether that water has polluted our drinking water or not. So in terms of protecting our environment, sensing of these heavy elements that are detrimental to specifically health of living organisms. These are very, very crucial, and that's why we need sensors which can perform very well to detect these pollutions or detect these analytes present in water at a minimum level possible, and also with a higher level of selectivity of this kind of devices. This gives you an overall distribution of simply the distribution of fluoride in Madhya Pradesh. So this picture is taken from MP Pollution Control Board Narmada, published in 2018. So in which you can see the regions of Jabalpur is actually having extremely high amount of fluoride concentration in groundwater. And remaining area like Betul, Harda, Devas, Sajapur, Ujjain, and many other places, they are also having limitations and also having very much effects, or the groundwater level, they are affected by fluorides. So we did a survey whenever we are trying to develop a fluoride based sensor. So that time we have diagnosed only one state of Madhya Pradesh, and how fluoride, that is mostly coming from the pesticide used by the farmers, are affecting the groundwater and eventually the soil health. So we could find out the maximum amount of degradation of the groundwater is happening in Jabalpur. And whenever the groundwater is polluted, obviously, whenever the groundwater is mixing with the river water, so generally it is causing a lot of problems with all the people and the living organisms, or maybe the trees and many other agricultural lands which are surviving due to the water of those rivers. So whenever we conducted this one, we just got to know about this picture, so you could imagine that how well and how crucial is it to develop a sensor to detect the specific amount of such concentration of analytes in water. Okay, and some of the other areas in which we have done a survey from different agencies from the Indian government, which are marked in this slide at the bottom of the slide, that the concentration of lead, fluoride, and mercury in different districts, specifically located in different parts of Madhya Pradesh. So you can see that the level of such heavy elements are extremely or beyond the permissible level that is required. And real-time monitoring, not only the diagnosis of the toxic elements present in the environment is necessary, but also it is quintessential to develop a system by which remote sensing of this kind of pollutions or pollutes in the water is necessary, and which you can measure and analyze on a real-time basis. So some of the commercially available products are there in the market which you could buy, but mostly these commercially available sensors, as you could see, like we could find out the point of contact sensor for measuring heavy elements in the water. They use by changing of the colors point of contact sensors, and some of these lab-based sensors also, those are available. But if you look at the cost of these two sensors, one is 20 USD and another is roughly around 350 USD, readily available test kit to detect contaminants, including heavy elements such as lead, manganese, and many other products in water. They are available, but the limitations in this type of sensors are they are extremely low in terms of selectivity. They do not give any quantitative estimation. They would be mentioning that yes, the water is having or it is polluted due to mercury, lead, cobalt, but exact amount of quantification is not available. Sometimes, mostly, whenever you're going to the market and buy this kind of sensors, sometimes they sense by changing of the color, which is called the colorimetric sensing. But sometimes by the perceptions of color, it is very difficult to identify which type of sensor it is looking for, whether it is detecting lead or whether it is detecting mercury. Sometimes it is very difficult to understand, depending, because it is also an experimentations with the quality of eye or quality of a human eye. And another limitation is no real-time measurement. So one time it is just touch and go. So one time you insert a strip and you say it is polluted due to mercury, but no real-time measurement, like how the mercury quantity or the pollutant is varying with respect to time. And on this type of sensors, also some of these limitations which are depicted for colorimetric sensors, in addition to that, sometimes it takes few hours to even days. So basically, even if you want to detect or if you want to make a remote sensor and do some real-time analysis, so you want to have the detection in quick manner, in a matter of seconds or maybe tens of seconds. So sometimes the sensors are available which generally take few hours to even days to attend and give you specific results. So in addition to whatever we have discussed over here, some of these problems are also there. So that's why we're looking for a solution which could alleviate all these problems. And of course, there has been, emphasis from different schemes from Government of India, like National Rural Drinking Water Program, Swasth Bharat, National Health Mission, Swachh Bharat, Namami Gange. So the motivation is remaining the same, to look for solutions which can deal with the environment quality betterment, to reach with the development of IoT-enabled sensors, which can not only detect the type of pollutant that is present in the water, but can also perform the real-time measurements and provide solutions out of it, how to get rid of this kind of pollutants in the water. So there has been tremendous emphasis from Government of India to develop, this kind of sensors and implement it for the betterment of human life in the rural area as well as in the urban area across the country. So if we try to concentrate on the type of gas sensors or VOC sensors, volatile organic compounds, so basically, if we do a survey on the literature which are present in the commercial area or in the industry scale as well as in the academic scale, so those are mostly classified based on the type of detection based on which these sensors do operate. So sometimes the sensors operate by the change of capacitance value or the sensing material. Those are known as capacitive sensors. So sometimes they do change with respect to the change of color. They are calling the colorimetric sensor. Sometimes they do have a change of potential that is applied across both the electrodes inside a sensing material, so potentiometric. So in that way, there are several different occasions in which you'll be developing a number of different sensors. If the change in the optical constants, be it a dielectric constant parameter change or be it the change of reflection coefficient or transmission coefficient, we call it optical sensors. Sometimes we do develop a transistor, a three-terminal based device in which the gate terminal is actually functionalized by using a typical sensor layers in which whenever the analyte comes with contact with the channel material, so some changes in the conductivity in the channel happens, resulting in the change in the drain current in the transistor, so field effect transistors. So those we call field effect transistor based. So sometimes we use short-tooth based if there is some change in the acoustic wave or any of the parameters that an acoustic wave may be having. Those are SAW based. Okay. So depending on all this, we have different classifications of the sensors. But the sensors which we are trying to develop, we are trying to look for solutions which we can develop in terms of or which should be having a higher value in terms of the commercial development. So that's why we're looking for a solution which is extremely cost effective. So that's why looking for a sensor mostly in the resistive way or maybe in the capacitive way. So today, the example that I'll be sharing with you will be mostly giving you a picture in which we have developed number of sensors. Out of those few I'll be presenting today in front of you. Those are mostly based on resistive sensors. And the resistive type of sensor, the schematic diagram is quite simple. Basically, you'll be having two different interdigitated electrode, IDEs, we call it in short. And in between two electrodes, we give a potential depending on the requirement and depending on the geometry of the IDEs. And on top of it, we just develop or deposit the sensing layer which we manufacture or which we design at our end, specific to a particular analyte. Okay, and this entire IDE and sensing layer on top of IDEs are established maybe on the flexible substrate, or maybe on silicon substrate, or maybe on glass substrate, depending on the applications. Right. So if you look at the literature, one will be able to understand that over the last several decades, many different sensors have been, if you're looking for the inorganic based sensors, so many sensors have been developed in which mostly metal oxide semiconductors are used. There has been huge number of transition metal oxide are used, like tin, zinc, tungsten, niobium, gallium, so on and so forth. So many others, those are reported in the literature, and this is overall the distributions in which you can see, depending on the color code, like which type of transition metal is used by many people, or which transition metal seems to be much more popular in terms of usage to develop such kind of metal oxide based sensors. So this is taken from this particular review article. So the interested participant may also refer to the same. The advantages of the MOX based or metal oxide based biochemical sensor is that it becomes stable, quite stable in terms of behavior, because the chemical nature does not alter. It becomes sensitive to analyte fabrication method. This is very simple. Either you do some kind of chemical deposition method, or maybe some physical vapor deposition, maybe sputtering. So the deposition system is quite simple, and large number of detectable gases depending on what kind of MOX you use as a sensing material. But which things you are actually having drawbacks in this kind of sensors? They are having a drawback in terms of selectivity. So basically the thing I was telling you about, if you want to detect a particular analyte in the presence of one analyte, in presence of another, it becomes a problem for MOX based or only MOX based semiconductor. And operable temperature. Sometimes it has been seen that operating temperature is beyond 100 degrees of centigrade. So whenever you try to develop this in the commercial area, and if you want that this should be a translational research work, not only laboratory scale research work, then you have a problem. That if you're looking for a portable sensor design, then actually on the sensor platform, you also have to integrate a mechanism by which the optimum temperature of operation is raised to that particular level in which this sensor material works perfectly. Okay, now there are several growth systems by which these MOX materials or maybe MOX nanoparticles are generated. One can be a physical route, like you can process by using sputtering schemes. Some of this also will be seeing today. Like totally, this is the physical way of deposition of materials. Sometimes we do follow chemical route of synthesis. Simply chemical reactions is happening in a wet chemistry lab, and we end up depositing our sensing materials. And sometimes a combinations of both or physiochemical route. We do carry out hydrothermal growth of synthesis. So each and every route of synthesis of such sensing materials, they do have some pros and some cons. So let us now go and see how we can actually do it in our lab. So these are the two different in-house sensor setup. These are mostly designed by our past PhD student, Vishwajit, who is now in CAS Lucknow. So this is the VOC sensing system setup that we have established in our research group, and as well as the gas sensing setup. So the typical identification of typical setup is very simple. So we have a chamber in which we just have our integrated sample, and there is a mechanism by which we can collect or connect the same with a Keithley source meter, or rather in any source meter. So basically you apply some DC voltage and you have some background generation of current by which you can get to know what is the best resistance, and simply you send out your VOC with a measured ppm that is calibrated by the MFCs. You can see the mass flow controller in both cases. So by the programming of this one, you can get to know what kind of analytes or what is the concentration of analyte you are sending in your chamber, And then depending on that, there is some change in the resistance value of the sensing material, or maybe the capacitance value of the sensing material, and you get to measure the change, and based on that you calibrate the sensor. Okay, so first, the example that I'll be sharing with you is regarding carbon dioxide sensor that we have actually developed in our lab. So if you're looking for a standard OSHA permissible exposure limit, like Occupational Safety and Health Administration, OSHA standards, so always whenever we are trying to develop a sensor, so OSHA standard, there are many other standards also that is available and followed in general, but OSHA is a very standard, platform or standard convention that is followed in the domain of sensors. So as per as OSHA PEL, the maximum permissible limit is 5,000 ppm of CO2 for human health. So in this case, even though there have been, like earlier, before we developed this kind of sensor for CO2 detection, there had been sensors, but as we have mentioned, that our motivation is always to look for enhancement of selectivity and sensitivity to carbon dioxide, as well as having a solution in which the sensor works perfectly at room temperature. So in this case, what we have done, we have developed a hybrid material by using a MOX based on zinc and by the usage of an organic compound, which is pi conjugated amine, based on our collaboration with the Department of Chemistry at IIT Indore, with the research group of Professor Apurva Das. So some of these examples and some of these investigations that we have carried out, that I'll be sharing with you for the development of this kind of carbon dioxide sensor. So this is the typical Nmr spectroscopic results, which shows you the molecular structures of the pi conjugated amine, in short, or naphthalene based pi conjugated amine. So in short, we'll be talking or terming it as NBA. So this is the final structure about how the polymer will look like, and this is the synthesis process, that how we have actually generated this pi conjugated amine by a number of different chemical synthesis routes. And this is the field emissions calculated micrograph about how these NBA nanoparticles look like on a 200 nanometer scale, if you could see. So why you are looking for pi conjugation? So basically, as I have told you, that we are looking for some solutions in which the sensing material should actually be capturing a particular analyte in the presence of many other analytes. And if we are successfully able to do it, so somehow we need to have the conductivity parameter, which is the basis of resistive sensor, to be controlled by this kind of selective capturing of analytes. So that's why we have observed that the presence of pi electrons, and if we somehow can control the density of pi electrons in the NBA, it actually helps us to capture CO2, the compound, intercompound, with the help of NH2 that we have over here. It captures CO2 very easily, and then it changes the conductivity of the material. And that is what we can see in the performance of this kind of sensor. So selectively it captures the molecules by making covalent bonds with CO2, and then eventually it deals with the variations of the sensor material conductivity. And that is actually our motto. And this is actually the synthesis of the hybrid material. So we followed the physiochemical route. So once we have developed NBA nanoparticles, so after that, we try to mix it with zinc oxide, or that is the MOX material which we have tried to use in these cases. So number of different, studying with HMTA, like hexamethyl, so HMT, as well as, by taking it in the Teflon lined autoclave and doing a number of different syntheses with respect to how high the temperature can be raised on a particular autoclave, and taking it for, or depending on the reaction time that we can allow for reaction to happen between zinc oxide and Nb nanoparticles, we end up having synthesized this kind of hybrid material of NBA and ZNO nanohybrids. So this is the schematic of this material, in which you could clearly see this is the IDEs that we have developed, and this is the schematic structure of how NB and ZNO nanohybrids are deposited on top of these IDEs, and this is the real-time image about how flexible the sensor is, because it is housed on PDMS, polymethyl disiloxane. So depending on the flexibility, one, you can easily bend it, because our ambition is also to make a wearable sensor, in which these are working with our counterpart at RMIT University, Australia, because they have developed this flexible substrate for us, and then they send it back to us, and then we develop the sensor and do calibrate and do the measurements for all type of sensing activities. So the IDEs that we have developed is based on chromium and gold, roughly 20 nanometer of chromium and 200 nanometer of gold IDs. So these are followed by standard photolithography process and E-beam evaporation technique at RMIT, Australia. Okay, so these are the hybrid material which looks like these are the morphological investigations carried out by FESEM, depending on the reaction time that is placed whenever the hybrids are placed in the autoclave at 95 degrees centigrade. So we could see as soon as the reaction time is enhanced, so the uniformity of growth is actually attained. And the nanohybrid diameter that we are actually getting is roughly 1 to 1.2 microns in terms of the diameter, and the length is very large. It is roughly 2 to 3 microns. And this is the zinc oxide nanorods, which we have separately manufactured with the help of the hydrothermal growth, which looks a beautiful, hexagonal shaped, rod-like structures. And this is the Hftm images, which confirms the hexagonal shape of hybrid formations of such NBA and zinc oxide based materials. And these are done by our collaborator at Shinshu University, Japan. And this is the electron diffraction images. So those actually satisfy that the polycrystalline growth nature of such hybrid material. And of course, in addition to do the morphological and the interfacial characterizations, it is also need to know the XRD, like basically the structural as well as the elemental composition. So from the elemental composition, EDX spectroscopy we did, energy dispersive X-ray spectroscopy. So all the elements that is supposed to be present in NB as well as zinc oxide, those are seems to be present also in these cases. And the same thing is also replicated whenever we are trying to see only zinc oxide XRD as well as NB nanoparticle, and the same features are seen to be holding true whenever we are trying to make this hybrid material of NB and zinc oxide as well. So this satisfies that whenever we are trying to make this hybrid material, the individual characteristics of NBA as well as zinc oxide are retained. And this is the typical growth mechanisms, which is actually analyzed and satisfied by the different analysis of morphology as well as interface as well as the structural and elemental. So we just developed these growth mechanisms, that how the process of conglomeration of this kind of NBA zinc oxide nanohybrids are carried out. So basically the NH2 bond which is there in the NBA molecule, those are there to bind with carbon dioxide that I have already mentioned. So basically the same seems to be true whenever we are trying to see the morphology by using FESEM as well as by HRTM. So similarly, that is also mentioned over here. So first, it is the nucleation, assembly, and the formation of nanostructure. It happens whenever we are trying to manufacture zinc oxide based nanorods. And then whenever we are trying to connect it with NBA, so the formation of this kind of petal-like structure, which is also schematically shown like this one, happens like this. Now looking at the sensing performance. So what this structure is telling us, that we are just trying to see whether the current value is getting changed. Because if we are trying to make a sensor, or basically a flexible sensor, first you also need to know about your background. So depending on the bending diameter, you just need to calibrate whether there is any change in terms of the device current or not. So we have observed there is negligible amount of current even if the bending diameter enhances from roughly to flat, that is no bending at all, to up to 20 millimeter of diameter. So there is no change in the device current. So that means it works perfectly, and the sensing material are actually having good adhesion with the flexible material. So even if there is some minor changes happen during the sensing performance, it is obviously not due to the bend condition of the flexible substrate. Then we do carry out the dynamic responses depending on different levels of carbon dioxide that we insert in the chamber. So we could see the dynamic performance of the sensor is extremely good. So even if we are changing the carbon dioxide concentration from 500 to even 10,000 ppm, the sensitivity kept on, or basically the resistance value kept on rising. That is perfect. That is what we want to see. So if we look at the comparative analysis also, like why the sensor response we are getting high basically. So whether the sensor response is coming only due to zinc oxide or coming only due to NBA, or it is also dependent on the hybrid. So here, when we did the comparative analysis, there we could find that with only zinc oxide nanodots when you are using, the response is quite minimal. It enhances for NBA, but it is the maximum when you use the hybrid material. So the maximum response of roughly 21% is obtained whenever using 2000 ppm of CO2. So we did the comparative analysis as well. And of course, whenever we are trying to have the response, we are trying to fit with number of different mathematical equations to plot a number of different components and find out different parameters that is responsible or to calibrate this kind of sensors. So I'm not going into the mathematical details of such analysis as of now. So we are concentrating mostly about the beautiful nature and the beautiful sensing and selectivity performance about this particular sensor. Now, as you could see, that this sensor we have tried to sense in the presence of other analytes, like another carbon related analyte is also there inside the chamber, that is carbon monoxide. Sulfur related gas is also there, hydrogen sulfide. Nitrogen related gas is also there, but in comparison to all these, the selectivity is extremely high for this type of sensor towards carbon dioxide. So roughly 91% selectivity, and this is a world record. So this has never been done for any other sensor till date on such kind of material on a flexible platform. So that's why we are very much enthusiastic to take this onward for the commercial development of this kind of sensors. And we have also tried to see the repeatability, because this is another aspect, as we have talked yesterday about the repeatability nature of the advanced memory devices. So the repeatability is also desired for sensing networks as well. So again, we have tried to bend it, and we could see there is hardly any change in terms of the sensitivity or in terms of the response that we could calibrate for carbon dioxide sensors. And always for commercial development for the sensor, since it is to be applicable in a humid environment in which it is not a laboratory environment, so the humidity effect also needs to be studied, whether there is any degradation in the quality and the sensitivity when the sensor comes in contact with the water present in the atmosphere. So we could see, even if the humidity is enhanced to roughly around 86%, so hardly any reduction in the sensitivity, only some minor changes in the response that is attained. And the response and recovery times are also quite good for this kind of sensors that we can see from this figure. And typically the carbon dioxide sensing mechanism, as I have mentioned, also schematically shown by this diagram. So obviously the ammonia bond that is existing in the NBA particle, it caps hold of this carbon dioxide and ends up, raising the resistivity of the material. So the presence of such heterojunction, basically the P type of NBA and N type of zinc oxide, increases resistance of these hybrids in the presence of carbon dioxide. So that is also schematically we have presented. And always, whatever results you could obtain, it always has to be compared with the many others reported in the literature. So as you could see, in terms of response or even selectivity or even lower value of carbon dioxide sensitivity, the performance of our sensor is very good. So we have published this work in 2018 in ACS Applied Nanomaterials. So interested participants may also refer to this particular paper for more information. Okay. So this is the carbon dioxide sensor and the development of a material towards, raising the selectivity of carbon dioxide, which you could see that it did not work for another carbon related product or carbon monoxide. So it is perfectly and specifically suited to selectively sense carbon dioxide. Now we have also carried out, and I'll also be sharing another picture with you in which we have tried to develop a carbon monoxide sensor, in which the OSHA standard is also more dangerous in terms of the PEL limit in comparison to that which was existing for carbon dioxide. So in this case also our motivation remains the same. We're just trying to enhance the selectivity and sensitivity and looking for operation, that whether we can reduce the operating temperature lower and eventually whether we can do room temperature sensing for this kind of sensors or not. So in this case, again, a hybrid material or hybrid sensing material is developed, but in this case, it is not NBA, but in this case, it is organodibenzoic acid. And this typical final product of this compound is depicted over here. And this is the FeSEM, morphology of this kind of organodibenzoic acid, which is synthesized by typical chemical routes, which are mentioned over here. So all these structures are again specified in terms of our calibrations and analysis by using NMR spectroscopy, which reveals the molecular structure. Okay. So again, the understanding remains the same. We are trying to use, sticking to our old transition metal oxide, which is zinc oxide, obviously in the case. So now here we are just trying to show you preparations of 4 different hybrid materials, or rather 3 different hybrid materials. One is without, any type of ODBA. So first sensing material that we have developed is having only zinc oxide nanoparticles, which we have earlier manufactured as well. And the second sensing material is that we are just trying to use separately manufacture a synthesized 10 milligram weight of ODBA into zinc oxide nanoparticle. We are terming it as OZ10. And we have tried to enhance the content of ODBA into the mix, 50 mg, 100 mg, so on and so forth. And similarly, we have also depicted OZ15, OZ100. And this IDEs, this time we have developed in collaboration with our counterpart at CSIR CD Pilani on Corning glass substrate. The typical camera image which tells you about the structure, which you could see in this screen image. And this is the FeSEM image in which the sensing material is actually developed on top of the IDs that you could see the linear scale image over this. And this is the schematic structure about the IDs that we have manufactured. And in this case, the IDE is based on platinum electrodes by using standard photolithography and electron beam evaporation for the deposition of platinum. Okay, so these are the hybrid material morphology that you could see. It is like mesh-like structure or net-like structure in that sense. And this is the typical schematics that we can come across after looking at the schematics of the morphology as well as NMR spectroscopy, the similar schematic that we have mentioned in case of NBA and zinc oxide. So for ODB and zinc oxide also, we have given similar kind of schematics that you could see in this case. The XRD confirms that the compound of ODB and zinc oxide retain the qualities that we have formed for ODBA as well as zinc oxide separately. And the EDX spectroscopy tells us that the elemental compositions what we had in ODBA and zinc oxide is also retained in the hybrid material. So in this case, since it is more like a porous structure rather than a petal-like structure, when we have formed the NBA ZNO hybrid in the earlier case of carbon dioxide, since it is more porous-like structure, so we have done some more analysis about how we can get to know about the surface area. So we have done the BET surface analysis, in which we have found out the average pore size of roughly 16.5 nanometers. And also we have carried out TGA, thermogravimetric analysis, in which it says that if we go beyond 140 degrees centigrade or so, there is huge loss of water from the ODBA, and eventually the hybrid material lose its nature. So basically, whatever the sensing material we're trying to develop based on this hybrid, those will be acting true till we reach 140 degrees centigrade or so. Beyond that, the hybrid sensing material to detect carbon monoxide will not work at all. Now, looking at the performance of the sensors depending on the content of ODBA, we could see the performance of OZ50, in which we have 50 milligram of ODBA in zinc oxide nanoparticles that we have generated, that performs the best in comparison to others. So now we have carried out our all other experiments. As soon as we got the performance of this sensor is the best in case of OZ50. So our next experimentation, we have concentrated mostly on this particular material or this particular hybrid material of OZ50. We have also done the effect of temperature on different type of sensors, and we could see that roughly around 125 degrees of centigrade, the sensor material works the best. Even if it works perfectly even at room temperature, which is, you could see this is the room temperature operation for all this hybrid material, and this is the room temperature operation for the case in which only zinc oxide is used. So the room temperature operation is also enhanced hugely. So it was roughly around, if you look at the response, it is roughly around 1 or 2%. And if you look at the performance at the room temperature for OZ50, it is roughly around 14%. So almost 7 times larger in comparison to the response that we had, in which we are trying to use only zinc oxide based. And the response has risen to roughly around 35% if we try to change or enhance the temperature to up to 125 degrees centigrade or so. So that means this type of sensor has capabilities to perform very well at room temperature sensing, as well as the sensing response enhances if we try to even enhance the optimum temperature or the optimum device temperature. So what we did in this case, we're just trying to see the impact of the transient response. So basically we tried to see the change of the analyte gas concentration from 5 ppm to up to 500 ppm. So we are seeing periodically the sensing response is also changed, which is also always expected for this kind of sensor in this case. So this acts perfectly true that this is a repeatable and reliable sensor to sense carbon monoxide. And in this case also, we have done the stable response, or we could see the step response change also, which we have calibrated, like starting from 5 to 100 ppm, and eventually we have, whenever we try to enter air, then the response reduces. So the step response also shows us that the sensor is quite stable to exposure of 5 to 100 ppm of carbon monoxide. Now looking at the selectivity, now we could see that this sensor sends towards carbon dioxide at 2000 ppm is this much. This is the value of response that we have obtained. And to carbon monoxide, even 100 ppm, this is a huge leap. For nitrogen related product, even if we enhance the concentration by 3 times to reach up to 300 ppm, is minimal. For sulfur related, also minimal. So this is quite selective, and the maximum selectivity is up to 88% in terms of the next highest selectivity of the sensor, which is the nitrogen related product, that is the ammonia in this case. So 88% selective to only 100 ppm of carbon monoxide. Okay, relative humidity effect also we studied, and we hardly see any change even if we have raised the humidity to up to 83% value. And we have tried to see the repeatability nature in the same concentration of carbon monoxide. It seems to be behaving the same way with respect to time. The transient response and values of the response and recovery times are also very good. 91 seconds for response time to basically detect and analyze, and 175 seconds to get it recovered whenever it is entered, or basically a new environment, or maybe the synthetic air is entered into the chamber. So it becomes available for sensing the next analyzed gas, whichever has entered into the chamber. So it is quite good enough. And also always it is dependent on the ID geometry. Like those who are already well aware with the sensing or basically resistive type of sensors fabricating at their own labs in the institution, they should be well aware of the fact that the response and recovery time is always a function of the contact geometry. So that is what we have obtained in specific to the context that we have developed till now with our collaboration at CSIR CDP Learning. And this is the sensing mechanisms also, in which the carbon monoxide is affixed to this open covalent bonds that we are having for ODBA for both the sides. So carbon monoxide is also joining hands by making covalent bonds and thereby enhancing the resistance of the hybrid material whenever the sensing material comes in close contact with the analyte. And again, we have done the analysis in terms of the performance comparative or performance comparison in terms of the carbon monoxide concentration, response value, response recovery time, selectivity. In those aspects, the performance of this system is extremely high in comparison to many others which are reported in the literature that we have found. The detailed analysis and idea about the sensing mechanisms are all depicted in our published literature that we have done or published in 2020 in the Journal of Physical Chemistry C. So the interested readers may also refer to the same journal. So as of now, I have shared with you two of our most recently developed sensors based on carbon monoxide and carbon dioxide, which are very, toxic pollutants and causes pollution to the environment in terms of gases that I have shared with you. So now what we'll do, we'll give a short break and we'll be meeting at 10:10 so that you can also have a short tea break or coffee break. So we'll meet again at 10:10, so 10 minutes roughly from now. So I can take few questions if you have on the topic which I have covered till now.
Sir, I'm Chandrasekhar.
Yes.
Sir, fantastic, sir. Good work, groundbreaking work, and everything is good, fine. Sir, I'm having small clarifications required.
Yes.
Sir, actually, here we are trying to do some kind of single composition. We are trying to develop some sensors for single compositions, right, sir? Like carbon dioxide and carbon monoxide and other things.
Okay.
So generally, what challenges we will face if we want to measure the composition of a mixture, like let's 2 or 3 compositions of a mixtures or gases. What kind of challenges generally we will face here?
Okay, so basically you're looking to make either an array of sensors. Basically, if you're trying to sense a number of different analytes simultaneously.
Yes, sir.
Or
Yes, sir.
if you're trying to sense only carbon related or maybe sulfur related products amidst the presence of any other analytes. So
Yeah,
basically, which one you are looking for, to make an
just
array of sensor, or looking to specifically sense a particular analyte in the presence of many others?
I'm looking for the array of sensors. I wanted to know all the compositions details.
If you are trying to make an array of sensors, so basically first you need to find out and basically develop your materials. For example, we have shown you that specifically we have designed two different organic compounds, and we have mixed and made a hybrid material which are extremely selective to carbon dioxide and carbon monoxide. Now, after you establish these two sensors, so then now you'll be able to think that how these two sensors are coupled in the same portable network. So for that, you are looking for a solution depending on the resistance change in the sensor. So for example, if the resistance change in the carbon monoxide sensor, if it happens between hundreds of megaohms to few gigaohms, so you're looking for a solution, because you have to do some microcontroller programming also, which I'll be showing few glimpses, in which you are trying to develop how we can also give rise to microcontroller programming, and we can actually sense it when you are trying to develop the portable sensor. And if this change in the resistance value for carbon monoxide, if it is way different than carbon dioxide, then your programming should be robust enough that you need, whenever you will be trying to integrate both these on the same portable network, because your same portable network should be having a fixed value of the DC bias, obviously, because you'll be connecting to a particular battery. But in the particular battery, if you add, then you should be able to know that what level of sensitivity you are expecting. If you're trying to develop a sensor for carbon monoxide, which sends from hundreds of megaohms to few gigaohms, and if your carbon dioxide sensor works from hundreds of kiloohms to change to 1 megaohm, so basically you're looking for a solution in which your resistance readout circuitry should be able to read from hundreds of kiloohm to 1 gigaohm.
Yes, sir.
So that becomes the most important challenge whenever you are trying to develop and integrate both these systems on the same platform. So that is the main challenge whenever one tries to develop a integrated more number of sensors on a network.
Yes, sir.
So this solution is not available in the literature, or also like our group has been working to solve it. So till date, we have tried, or we have successfully developed, in which we try to sense, like if it is hundreds of megaohm to even few gigaohm, we can calculate and we can do the calibrations of a readout, resistance readout circuitry. So some of this also will be presenting, and my student will be presenting in today's afternoon session. But we are trying to see how high we can go, whether we can widen it up from hundreds of kiloohms to even gigaohms. If we can do it, then the commercially development process becomes very easy. Because sensing research and development is still thought to be one of the easiest way to do some research. But as long as you're doing in the laboratory, it is okay. For publishing paper, it is okay. But if the motivation is also for translational work, that becomes a challenge.
Yes, sir. Thank you, sir. Thank you, Professor.
Yes, thank you.
Sir,
any other questions?
Sir, there is a question in the chat box.
Okay.
Dr. C.R. Menitha is asking, is it any precautions measurement we have follow working with CO gas?
Yes, it is quite detrimental. So that's why the exposure limit of these gases you have to precisely control in the laboratory scale. So that's why even if you try to or plan to procure carbon monoxide, generally what we do, we procure the gas cylinder specifying what should be the concentration of the carbon monoxide in the synthetic air. So by that way, we just, during the procurement only of these cylinders, we just specify this value to the commercial industry. So the similar way you could also follow, because the exposure is hugely detrimental.
Yes, sir, thank you.
Yes. Any other
No,
questions, Sumit?
no, sir. I think till now,
Okay,
no.
so we can give a short break then. So right now it is 10:05. We can meet roughly around 10:15. Okay, okay. Yeah, thank you.
So now I request all the participants, please switch on your videos because we have to take a screenshot. So please switch on all the participants, please switch on your videos. Again, I request to all the participants, please switch on your videos. Just some more participants can switch on their videos, then we can take the screenshot. Don't know why the participants are not making their video on. Dr. Sunil K. Singh, Dr. Upma Jain, please switch on your video so we can take the screenshot because we have to upload these screenshots on the ATAL platform. Without these, the report will not be completed. And if report will not be completed, it will be very difficult to generate the certificates. So I request all the participants, please switch on your videos. Okay, you can switch off your videos. We have taken. Thank you. Thank you all for the.
Please unshare your screen. Okay. Okay. So can you see my screen?
Yes, sir, we can see. It's
Okay. So welcome back. So before the short break, I have shared with you about 2 glimpses on the development of gas sensors, mostly carbon related sensors. So now I'll be sharing with you some of our recent activities also after this one, because here I'll be sensing or giving a glimpse of our VOC sensing research that we have done a while ago, in which we are trying to see the ethanol sensing performance based on only the metal oxide semiconductor. So they do not have any combination with respect to an organic compound. So in this case, we are trying to use molybdenum oxide. So after this one, then I'll be sharing with you some of our most recent work that we have done to sense sulfur related or even nitrogen related products, and the work on 2-dimensional transition metal dichalcogenide systems that we are pursuing or we are carrying out currently in our group. Okay, so anyhow, starting with the ethanol sensing. So here, actually our motivation towards this research work is to increase the amount of defects and surface area, basically trying to see what kind of nanostructures we can manufacture in molybdenum oxide, that is the transition metal we are trying to use for this particular sensor, and whether we can play with the geometry of it, and whether we can play also with the surface to volume ratio during the growth and synthesis process of molybdenum oxide nanostructures, and thereby whether we can or how far we can play with the sensitivity and selectivity parameters towards ethanol. Okay, so here what we have done, this is the typical hydrothermal synthesis method we use for the generation of molybdenum oxide semiconductors in these cases. And while using this salt and after immersing it with nitric acid inside the autoclave, the temperature of excitation, or basically the reaction temperature, we have modified in this particular reaction or synthesis process of eventually resulting or giving away with molybdenum oxide based nanostructures in the form of bells and fibers. So typically 8 different schemes we're just presenting over here, in which we have tried to play with the reaction temperature while this salt along with the mix are kept in the Teflon lined autoclave. Okay, so for sample or sensing sample number 1, we have tried to use 6 hours of autoclave operation at 120 degrees centigrade. For M2, the same temperature is maintained for double the time of the first one. For third one, we have just enhanced by 4 times. And for fourth one, it is just a multiplication factor of 2 that exists for M3. Okay, so that classifies M1, M2, M3, M4, in which the temperature profile remains the same, only the time is varied. Later, what we did, we have just tried to change basically the temperature and the room temperature. Basically, maximum temperature is 120 degrees centigrade, and we have just tried to change the elevation from room temperature to the maximum temperature of 120 degrees centigrade with respect to different amount of time. So what we have played with the slope of the line from reaching room temperature to 120 degrees centigrade temperature. So in that way, it is actually related to the variations of the time profile. So we are just calling it in terms of the frequency of operations for the changing of temperature for generating this kind of sensing material starting from M5 to M8. So in this case, as you could see from the schematics, that the maximum frequency is attained for M5, in which the frequency is roughly around 1/6 per hour. And the lowest frequency is for sample number M8, that is the final one, in which the variation is not that precise, or in that sense, it is not reaching up to a maximum frequency. Of course, it is the lowest frequency, and the value is 1/24 per hour. So we're just trying to see whether, depending on this pulsed temperature process, whether they do have any effect on the quality or the morphology that the molybdenum oxide nanostructures they do have, and whether eventually when we make the sensing material, they do have any impact or not. Okay, so for M1 to M4, it is the static temperature model. M5 to M8 is the pulsed temperature model. So what we have observed from the morphology, M1 to M4, whenever the reaction time enhances, we could see uniformity is enhanced. Okay, and for M4 sample, that is the 48 hours long sample that you also could see from this structure that we have presented in our earlier slide, that the uniform nano belt like structure you are able to see from the grass like structure for M1 or the M2, as you can see. And the nano belt width we have measured, it is roughly around 300 to 400 of nanometers. And for M5 to M8, we have observed whenever we are trying to reduce the frequency, that means whenever we are transiting from M5 to M8, uniformity, we are seeing it is enhancing. Okay. So at M8, that is with the minimum amount of frequency, uniform ultra-long fibers where we can see in these structures for M8 sample. And these fibers are roughly 200 to 300 nanometers of length. XRD represents very beautiful, and as we have observed that at the reaction time enhance, the crystallinity is also enhanced depending on the diffraction peak, mostly oriented towards 040 plane or 020 and its multiple planes. Okay. And so for M1 to M4, the reaction time, whenever it is enhanced, crystallinity is enhanced. And whenever the frequency is reduced, when we talked about the pulsed temperature profile, crystallinity is enhanced. So the highest crystallinity is attained for M8. In this case, the highest crystallinity is attained for M4. So in the inset, we're just trying to show you the diffraction profile or X-ray diffraction profile from M4 and M8. So out of the pulse temperature profile, crystallinity is the highest for M8, and out of the static temperature profile, M4 crystallinity is the highest. Okay, and if you compare both these, like all 8 samples, M8 exhibits the highest crystallinity. EDS spectroscopy always reveals molybdenum and oxygen in all our samples. Okay. Again, we have done the BET surface area analysis, and we have seen the surface area is roughly around this much, 4.48 meters square per gram for M8, means for the pulse temperature profile, and it reduces for the static temperature profile. Okay. And the temperature, when we get it from thermogravimetric experiment, that it sustains very well even if at a larger temperature, and this sustains mostly better for M4 sample. So whenever the MO3 nanostructure is formed using a static temperature profile, that seems to be performing better in terms of temperature of operation rather than the material or the sensing material which is deposited or which is synthesized using a pulsed temperature profile. Okay, and this is the Hftm analysis, in which M4 and M8 samples, they do show, polycrystalline growth from as it also can be ascertained from the SAED images. And M8 interplanar spacing along 100 and 001 is roughly around 0.39, 0.36 nanometers of dimension. Okay, so the structure is quite beautiful as ascertained from the Hftm as well as from the XRD images. Okay, now let us look at the performance. Since we have already seen that from the static temperature profile that the performance of M8 or M4 rather is the best. So while we formed the comparative analysis towards various VOC sensing, starting from ethanol, methanol, propanol, benzene, toluene, xylene, acetone, the performance of M4 is plotted along with the performance of M8, which is the best sample in terms of the dynamic temperature profile. But when you look at the performance of both these, the dynamic temperature profile sensing material, that means M8, behaves better in comparison to M4. Here the response profile of all the sensing materials are plotted, in which M8 always behaves the best, and the temperature of sensing seems to be roughly around 275 degrees of centigrade. Optimum temperature for M1 to M4, and for M5 to M8 is roughly around 300 degrees centigrade of temperature. Okay, so we have carried out the performance for transient repeatability measurements, and the sensing materials M4 and M8, they perform very well, as you could see from the measurements, even if it is exposed to only 200 ppm of ethanol. Okay, so the good repeatability and reliability is obtained for this kind of sensing materials. And when we calibrate the transient response for M4, the response time is 69 seconds and recovery is 174, and it is further reduced when we look at the profile for the sensing material which is prepared by using the dynamic temperature profile. So it is reduced to 45 seconds for response and 138 seconds for recovery. So we have done lots of calculations and also identifications about how, the resistance changes, the phenomena happens, and how, amount of electrons are also generated whenever it tries to sense a particular analyte, in this case, the ethanol, which is in the picture. And we have published this work in Material Research Bulletin in 2019. And we have compared the performance of our results in comparison to many others which are reported in the literature. So interested readers may also look for these values for more information in this particular reference. Now, the recent work which we have been pursuing, and we have recently also generated one patent out of it, in which we are just trying to show you another method of synthesizing a novel hybrids, which is based on carbon dots, which is prepared separately, and by the similar process of hydrothermal scheme, we are just trying to mix it with another transition metal oxide, which is tungsten oxide, in this case WO3. The process remains the same, and the mixing process also remains the same. So separately preparations of WO3 powder, and slowly and surely adding carbon dots or different types of weight into the mix, into the ethanol, and then eventually drop casting it on the IDEs that we can manufacture on the glass substrate. So in this case, the glass substrate along with the IDs come from our collaborator, RMIT University, Australia. So everything remains the same. And this material, we have seen that it works very beautifully towards sensing of nitrogen-related analytes. That will be seen also. And recently, we have just published one Indian patent out of it, and also submitted the paper in the journal, which is currently under the review process. So not only we have done the single stage or pristine amount of mixing of tungsten oxide into the mix, we have also tried to see the effect of doping into the tungsten oxide. So what we are trying to do, we are trying to add palladium into the mix. So the palladium into the mix happened on stage 2, as you could see, in 10 milliliter of nitric acid in the solution that we have prepared for stage 1, that was remaining the same whenever we are trying to add sodium chloride and sodium tungstate dihydrate, as we have prepared and as we have used for the preparation of WO3 powder. And I have showed you in the previous slide, that remains the same. So the calculation or the addition of palladium happens on stage 2 when we precisely added different weight percentage of palladium into the mix. And the process remains the same to eventually, let me go back, to eventually generate the palladium doped tungsten oxide powder. And this is the drop casting method, and this is the field electron FESM image as well as EDX spectroscopy that we have obtained and drop casted this particular solution into the mix on IDEs with glass substrate. The third scheme, not only this transition metal oxide only, we're just also trying to actually generate two-dimensional transition metal dichalcogenides in the form of molybdenum sulfide by a recently procured chemical vapor deposition system in our lab. So in the afternoon session today, actually my student Chandravan Patel will be discussing many things about this particular new development that is happening in our lab, and share with you some results and also some hands-on training over the virtual platform to be given to you about how all these things are also done. So this is the most recent work that we have been doing in our lab. So again, what we are trying to do in this case, so separately we have prepared molybdenum oxide solution in ammonium hydroxide, and that is also a precursor for the development of molybdenum sulfide. So we just spin coated the same on a substrate, and then we place it inside the chamber of CVD. So the substrate can be different. It can be sapphire, it can be silicon oxide coated silicon, or something else. And this is the typical geometry of the typical schematic of the CVD system that we have. Let me go back. So that we have with us, in which we can, by the usage of mass flow controller, we can vary the ambient and vary the pressure of the gas also that is used in this chamber. So currently argon is shown over here. So we can also use other gases also, for example, oxygen or something else. So depending on the growth kinetics and the chemical reaction that is desired to happen, so we determine the place in which the molybdenum oxide coated substrate to be placed, and the substrate on top of which the material has to be deposited, or the molybdenum sulfide synthesis has to be done, is to be carried out. So this is, you can see now the molybdenum oxide coated substrate is placed underneath, and on top of which the substrate is placed, in which we are supposed to see the deposition of molybdenum, two-dimensional molybdenum disulfide. And this is another setup in which on the quartz board we are just placing sulfur. So this specific CVD system, they have 12 different zones of different widths. So independently we can control the temperature of each such zone. So depending on the optimized condition that we have realized, so we can generate uniform and monolayer MOS2 nanoflakes deposited on top of substrate. So which is also shown by the microscope image in these cases. So this is the huge structure of the MOS2 nanoflakes, or large triangular flakes that you could see manufactured by CVD. And this is the number of different nanoflakes clusters around silicon oxide coated substrate. And the Raman spectra, as we, like many of us who are well aware of the development of this 2D TMD materials, they know that the Raman peak difference between these successive peaks, roughly around 370s and 400 centimeter inverse, if the peak difference remains between 18 to 25 centimeter inverse, then the resultant MOS2 is supposed to be, or known to be, having a monolayer in terms of structure. So that is what we could see in this case, because the peak difference is roughly around 21 centimeter inverse in our case. Okay, so once we successfully develop the depositions of 2D TMD, then we also tried to transfer the substrate on top of another substrate. So because we should be remembering that since our IDs are developed on top of flexible substrate or maybe glass substrate, so there should be a mechanism by which this entire MOS2, which is actually deposited on silicon oxide, silicon coated glass, or silicon oxide coated silicon substrate, whenever we are trying to transfer it on top of the IDs that is developed on the glass substrate or maybe on the flexible substrate, so there should be a mechanism, established mechanism, by which one can take out this MOS2 and basically put it on top of another substrate. So in this case also, our student Chandravan Patel, he has done it successfully. So by the coating and specific amount of optimized coating of polystyrene on top of MOS2, and then eventually using the water droplets, because MOS2 and silicon oxide, in terms of reaction to water, so one is hydrophilic and another is hydrophobic. So due to the difference in terms of nature of reaction to water, they can easily be poked out of it by this one, And by using a tweezer, one can take it out, the entire structure of MOS2 on top of polystyrene, and you can place it, one can place it on top of another substrate. And once that kind of substrate transfer is done, the polystyrene layer can be easily dissolved by using toluene solution. So one can deal away with polystyrene. Eventually, we'll be having OS2 deposited on top of the glass substrate or any other substrate in which you are having the IDEs which are made. So these are the typical camera image of the MOS2 which is successfully transferred on top of the IDEs on glass substrate in our lab. And this is the typical geometry. This is the typical geometry of the IDE which is developed in collaboration with our collaborator, Professor Sharat Sriram from RMIT University, Australia. And this is the schematic. And these are the different dimensions of the IDEs that is mentioned on this slide. And this is the typical schematic in which the 2D TMD triangles are actually developed or actually deposited on top of such IDEs. So first, if we look at first the result about the carbon dot and tungsten oxide hybrid that we have spoken the first, we could see that particular hybrid behaves extremely well for nitrogen related products in the presence of many others. So this particular material works perfectly for nitrogen dioxide or basically nitrogen related products, and even it does not only work for 100 ppm, for sub level of ppm also, like 250 ppb also, parts per billion, it also works perfectly. And please remember that these results we are just showing over here, these are the sensing results happened at room temperature. And if we look at the effect of temperature towards only 10 ppm of NO2, the performance at room temperature is quite good. And it becomes the maximum when the temperature is risen up to 150 degrees of centigrade. So as you could see, only for 1 ppm values of nitrogen dioxide, this sensor acts perfectly well and repeatable enough, even if we try to operate at room temperature with a relatively high value of humidity of 50%. Okay. Now, this is another sensor which I have not shared, but from our published results, in which also we have tried to develop another covalent organic polymer. We are calling it as COP, with respect to having some pyridine functionality. And this works perfectly when we are trying to diagnose or trying to make a sulfur-related analyte sensor. In this case, sulfur-related analyte sensor is hydrogen sulfide. So as you could see from the selectivity response measurement, that this works perfectly in the presence of other carbon-related and nitrogen-related analytes. The sulfur-related, like H2S sensing for 100 ppm values of sulfur, it is extremely good. So due to the time constraint, I am not able to give you the picture of it, but these are all from our published work. So the interested readers may refer to our website for more details about this publication. So this particular publication came in last year, along with the group of Professor Apurva Das in the discipline of chemistry of IIT Indore. And this response works fantastically. If we look at the dynamic response, and the response and recovery time is extremely fast in comparison to many others reported in the literature. And again, as you could see, these results, whatever we are plotting, in this case, all these results are valid at room temperature. So this is another step in which we are just going to develop this type of sensors for different type of analyte sensing for room temperature sensing applications for commercial development. Okay, and this is the palladium functionalized tungsten oxide that we have manufactured, and I showed you the results also. And again, this is oriented towards sensing hydrogen sulfide with respect to many others, and selective sensing basically of hydrogen sulfide. Okay, So this is also one of our work. So I'm just showing you some glimpses of many of the activities that we are trying to establish, but always our motto remains the same, because we are trying to establish a sensor which behaves very nicely at room temperature. It is repeatable and reliable enough, and it can be integrated, which I'll be talking about this slide later. So which can be integrated on a portable network and eventually can lead up to lower temperature of operation, specifically to even room temperature of operations. So the work that I have been talking to one of our guests today is actually trying to develop a temperature controller and resistance readout circuit. Like if you have a motto to have this kind of circuits or this kind of sensor to take in the commercial area. So this is just a preliminary work that our students have done, our undergraduate and master students have done. The simulation work on Proteus platform, and this is the resistance readout circuit on a breadboard. So once this circuit is designed, it has to be first seen how well it works on a breadboard network, and once that works perfectly, then we transfer it on the PCB. Okay, so earlier we have developed a resistance readout circuitry, so going back in 2019. So now we have also had advanced results, but due to the data security point of view, I'm not trying to share with you the results. Going back in 2019, we have developed a resistance readout circuit which could perfectly or suitably measure a resistance in the range of 1 kilo ohm to up to 20 mega ohm with less than 1% of error. So that is one of the first motto. So whenever you're trying to actually get to know or only try to make a temperature controller circuit, in this called resistance readout circuit. So here resistance readout circuitry we're just sharing with you. So it should be able to measure a wide range of resistance so that this can hold true whenever you're trying to integrate a number of different sensors on the same platform. So the commercial applicability becomes higher if you're trying to give a solution to the industry by showing or demonstrating that we have developed an resistance readout circuitry which can gives out the measurement of a wide range of resistance with minimal amount of error. So this has huge potential if one wants to work along with us also. Another phase of working not only related to only resistance readout circuitry, but another is the HEMT based circuitry, high electron mobility transistors that we develop in our lab, that is primarily based on zinc oxide and magnesium zinc oxide materials. So I'll be delivering a talk also tomorrow based on our work on this particular heterostructure towards HEMT applications. Okay, and these HEMT devices that we have actually fabricated successfully. So the functionalization of the channel, which is lying between the source and drain contact, we can also use a number of different functional groups. Those can attach with number of different analytes. Those are mostly oriented towards making water sensors that we have earlier also discussed, and eventually it gives to extremely high values of selectivity and sensitivity depending on what kind of functional groups of molecules we can make and we can associate with the channel layer. Okay, so the work is also going on this particular topic in our research group, in which our motivation is always to make an handheld portable device, okay, in which real-time remote sensing or monitoring can be made possible. Okay, number of different compounds are getting synthesized in collaboration with our colleague from the Department of Chemistry, in which number of different analytes also could be formed. And obviously, the final picture is raising towards the IoT enabling process in which real-time remote sensor or sensing can be done. So in which our purpose is to make the portable sensor, and in which it can be also connected to a microcontroller unit and integrated with a wireless transmission module, so that even if it is placed on a remote placing, So depending on the environmental pollutants on a real-time basis, it can be captured and data can be collected and stored in a cloud network. And SMS alert also can be generated. So right now on this work, huge amount of activities are being done in our research group. So if any of you are interested, you may also join with our group for different such adventurous works that currently our group has been doing in this particular domain of research activities. So we need expertise not only from sensing point of view, but the point of view of computer programming, microcontroller programming, integration, and also analysis in the cloud computing based knowledge. Like if you are well knowledgeable in this particular domain also, so you may drop me an email that you are interested to work with us. So there are possibilities we can also work in collaborations with you. And conclusions and opportunities towards this, obviously our main motivation is towards toxic gases and then VOCs, and heavy elements also we are trying to work, that is detection in the water. Yes, microcontroller based integrations, because our motivation is to reach towards the commercial development of all these products for real-time and remote sensing mechanisms. And in terms of material point of view, we are looking for materials which can be having extremely high value of selectivity, which was very fast, and high room temperature response. So we welcome participation from varied background or manpower exchange and joint collaborations. So we are open to all. So if you are interested, please drop me an email regarding this. So with this, I'm ending this topic now. So I'm now okay to answer any questions that you have.
Thank you, sir, for such a wonderful and informative talk. Participants, now floor is open for the questions. You can unmute yourself and ask your questions directly to the speaker. Any questions, participants? I think there are
Hello.
no.
Hello, sir. My name is Meeta CR from Coimbatore, Tamil Nadu. Can I ask question to sir?
Yes, definitely. Please go ahead.
Yeah. Thank you, sir. Actually, the informative talk and very much interested in your topic. Sir, actually, in my PhD work, I actually worked on the same thing. Actually, I work on the VOC sensing and then CO2 gas sensing and then strontium and cesium metal ions detection from the water. Okay, sir. Sir, but I actually I don't have any knowledge about IoT and those things. So is it possible to upgrade my research work? Is it can I want to initially I want to study some program kind of things, or otherwise what you are actually suggest me for do the next thing, sir?
Yes, definitely. So if you are interested to pursue your work
Yes, sir.
on heavy element sensing, probably in water, because already you have an exposure during
Yes,
your
sir.
PhD time, so you're more than welcome to pursue your work in this arena, because now you could see from
Yes, sir.
different schemes by Government of India also, there has been tremendous encouragement. Like if you
Okay.
can develop a sensor system
Okay, sir.
by which this analytes present in the soil or in the water, you
Yes, sir.
can sense it in a cost
Yes.
effective way. But always the emphasis, as you know, it is towards the commercial development of it. But at any point of time, if you have prior knowledge and experience in development of such sensors, even in the laboratory scale, those will be of primordial importance. So if
Okay.
you like to join hand with us, we are more than welcome to do that.
Okay, sir. So for IoT kind of thing, is it we are familiar of some other any other computer language or anything like that, sir?
So microcontroller level programming is what you probably need to know.
Okay, sir.
So then, because whenever we are trying to, like right now, we have just shown you one of the glimpses that we are using the Proteus platform. So there are many other tools also, commercially available tools you
Yes,
can
sir.
use. by doing, like if it is a resistance readout circuitry or temperature controller circuitry, we're just trying to use Proteus. So there can be many others also. So if
Okay,
you're
sir.
well acquainted with those tools, that might be beneficial. Because
Okay.
first is that is making your device portable. So once that is done, then it becomes that how you can transfer it or get the data in a wireless or maybe wired communication way and store it in the cloud network. So readily available apps are also there in the mobile network, or you can store in the laptop also. So the challenge that will be remaining after you integrate your sensor to the portable network, that how you can transfer the data to the cloud. So that part will be much easier. So
Okay.
first
Okay,
part that
sir.
will be challenging is how you can integrate your sensor to the portable network.
Okay, sir. Thank you, sir. I'm
Yes.
also working the volatile organic compound sensing like toluene and acetone, ammonia also. But my PhD work, I just kept like array sensing like that. But I didn't go for the upgradation that you are saying at a portable sensing like that. So I was willing to do, but I will contact you in future for this thing. Bharat.
Definitely.
Thank you.
Definitely.
Thank
More
you
than
very much,
welcome
sir.
to do so. Thank
Yes,
you.
sir. Thank you very much, sir.
Any other question? I think they are not questions from the participants. So thank you, sir. Thank you again for such an
Thank you, Sumit.
informative talk. So
So now we have the next talk is at 11:15.
yes, sir.
So you can put the screen, I think, for our next speaker, and let us wait to hear from him. That I got to know that he might not be having WebEx installed in his laptop. So if Professor Bhattacharya is unable to connect via WebEx, then we might to switch it to Google platform.
Yes.
So as of now, let us wait for him to join in this session only. And if he's unable to join by that time, I'll be having some telephonic conversation with him. So then we'll be requesting all the participants to join in the Google meeting.
Yes, sir.
Okay. Thank you, Sumit.
Thank you, sir.
Yes, I think Professor Bhattacharya has joined. Good morning, sir. Hello, good morning, sir. Yeah.
Good morning. Good
Yes.
morning.
Yes, sir. Thank you so much for joining. So, sir, I'll be giving a brief, details about you. Then I'll be leaving this floor to you.
Okay.
So, many welcome to all of you on session 8 on day 3 of this ATAL sponsored faculty development program. So, today we are fortunate enough to have Professor Kanti Bhattacharya from IIT Kharagpur with us to deliver his invited talk. So just to give you a brief details about Professor Kanti Bhattacharya, he has received his BSc honors degree in physics and the BTech degrees in radio physics and electronics from the University of Calcutta in 1984 and 1987 respectively. And then he pursued his ME and PhD degrees in the Department of Electronics and Telecommunication Engineering from Jadavpur University, Kolkata in 1999 and 1996 respectively. He has served as a scientist in the area of thin film technology and microelectronics in reputed laboratories such as the Indian Association for Cultivation of Science, Central Grass and Ceramic Research Institute, CGCRI, at Kolkata, and the University of Kaiserslautern in Germany. He has been a visiting faculty with the University of Washington, Seattle, USA, and the University of Michigan, Ann Arbor, USA. He is currently a professor with the Department of Electronics and Electrical Communication Engineering and the Advanced Technology Development Center, ATDC, in IIT Kharagpur. He is also the head of ATDC and the professor in charge of the Advanced VLSI Laboratory at IIT Kharagpur. His current research interests include low power radio frequency integrated circuit design, MEMS, and nanoelectronics. Professor Bhattacharya is also a member of Indo-US Frontiers of Engineers and the Indo-Japan Collaborative Committee on Advanced Micro-Nano Manufacturing Science. He has been a recipient of the UNIDO Vienna Fellowship in 1992 and the prestigious IBM Faculty Award in 2012. So, sir, I'm requesting you to kindly share your talk with us and enlighten us with your experience. Thank you so much, sir. Now the floor is all yours.
Thank you, Shaibal, for your nice introductions. And I'm pretty humble enough that really from 87 till 2021. So it is the journey of my research. So many fields have seen few decades of changes in the technology. And so it looks pretty interesting that from where I have started and at the moment what I am doing it. And I try to share a bit of it, that 2 hours lecture. I will try as much as possible to give in few areas, which is currently I have been working, and also some areas which I have touched upon and worked even a few years back. So both the developments and whatever I will speak out today is based on my own experience and what we have done in the laboratory. And if possible, I will show you a video documentary made by Durdarshan on my lab and my work. So that I will give you the live view of the lab and how the things are being developed. So again, Professor Mukherjee, it is my I am really feel happy and fortunate that you have given me that platform, and I wish that I have visited IIT Indore for in connection to some PhD viva, etc. So let this. I think that students here or the participants are mainly the faculty members of various colleges, and and also few senior level students, PhD students. So my approach will be pretty much touch the base and then start something. Okay. So let me share some of my work. I will come to the PPTs at the moment. Just wait for a second. I am sharing my presentation. Just wait. I am getting little confused. It is little bit change from my 1 second. Let me see. Yeah, can
Yes, sir. We
the
can see your
screen?
screen. Yes, sir. We can see.
Oh, wonderful, wonderful,
We can see the PPT.
wonderful. Yeah, PPT. So,
Yeah.
so I think good morning to all of you. I have decided to talk about the MEMS and its two primary applications which have been developed from a group is called painless drug delivery systems for it was targeted for insulin delivery, but now due to the COVID and other diseases, we like to make it for a vaccine, injectable vaccine platform, which will be painless, just like a patch. With this, and also another activity, the space application, applications. Before I speak the MEMS and the there may be questions to all of you of these miniaturizations and integrations. So if I ask you some questions to begin with, that if you want to buy a laptop today, it will cost you around 45 category laptop. Wanted to know that what price of this in such a direction that the cost of the product becoming less. And whereas if you want to buy a flat at Indore, and then you know that today if it prices maybe after 3 years, it can 20% rise. Maybe after 6 years, it will be 1.5 crore. So the real estate, that business is always in the increasing trends. But whereas in this real estate, the silicon real estate, the price is down. Even the price is the same, but more functionality and actually we
Sir, sorry to
it
interrupt you.
was a symbol of our
Hello, sir, sorry
we
to
are from the
interrupt
rich
you.
section of the system. Hello,
Sir, your voice is breaking.
hello.
Hello, sir, your voice
Oh my
is
God.
breaking, sir. We are not able to hear
Hello.
clearly. Hello, sir.
Then actually, hello. Yeah, I understand it, but what to do? Should I reconnect? Hello.
Sir, we
Sir,
are able to hear you now.
we are able to hear you now, sir.
Like
Hear
in
you now.
between, it was little
Okay.
getting
Then
little.
yeah. Yeah. So what is happening? That why this cost is going up in one technology, that is, if you look at the civil construction architecture, it is actually going up. Whereas this technology is technology, be it in the civil or mechanical or architecture, or in the electronics domain, the price is going down because of a simple thing, that in the microelectronics domain, we have been able to miniaturize the structure and keeping the functionality same, even more better. So mind it, that functionality. So only the miniaturization and integration won't help you until and unless the functionality will remain the same. So that is the underlying philosophy behind any microelectronics activity. So you have to be very careful that which technology where I can miniaturize and integrate, that will provide me a better functions or more cost effectiveness. Whereas in the civil, they cannot do that, right? They cannot make the reduce the size of the bricks. Then only the doll can actually live in, but not human being. So it loses its functionality. So only integration and miniaturizations will not only give you the scope for its advancement, but it will be more and more the functionality remains unchanged, or even we can increase it. So now if we look at, we are in almost hitting the Moore's wall, right? That is the every 18 months, the size is getting half, and miniaturizations and their integration every twice times every 18 months. So almost we are in the 3 nanometer node. So people talk about 1 nanometer. I'm not very sure. So almost we are hitting the wall. But so we are in the junction, which is called the more than Moore area. In the more than Moore era, that is exactly we are now at that junction. What is the main difference, which is 10 years, 20 years, 30 years before and now? That we are now trying to, along with its miniaturizations, we are now trying to include more number of functionality into the systems. So all of you know about uh, the the system on chip. So that concept is actually built up, say, 5 years before, but now it will be the main thrust in our technology node. That is where the CMOS, the power devices, the RF, the sensors, the lab on a chip for the medical applications, all will be integrated together in a single platform. If not in a single die, but in multiple die, but in a single package. So overall, we call it as a system on chip. So think of it
Hello.
that we are reducing the size as well as we are now trying to
Hello.
build up the system. Okay.
Sir,
The
again,
functionality we
hello,
are
sir.
increasing. Yeah. Hello.
Sir, again, sorry to interrupt
Hello.
you. Sir, yes, sir. We are still on slide one, sir. So slide is not changing, sir, I think.
Yeah. Yeah. So now I am with this technique. So we are finding out that the one of the experience is called, say, we want to develop microneedles and micropumps. I will talk about that to give drug delivery for human being. Okay, so what you will learn, that it will be first I will introduce, then I will identify the problems, then I also talk about the market overview. Then you know that people talk about biomimicking, but I feel that better word should be bio-inspired design. We cannot. So I will explain mean by mimicking the nature and what is the. Then we'll talk about the overview of a painless drug delivery system, design, fabrication, and characterization of hollow microneedle by batch manufacturing, which is very important. That how would you produce it for the market, and development of process, thoroughness, and biocompatibility, which is very important. Those who are interested in the biomedical space, they must be very careful. There are few still restrictions in the biomedical devices. I will, if I find time, I will give you the BIRAC chart of TRL levels and all, and what are the needs of medical devices, what kind of compare. Then I will talk about. So problem definition, and there are few we are already seeing in the device, even something like smartwatch. All of you know that mobile connection for the provide your health for the almost all statistics instantaneously. Even your sleeping mode of sleeping and all these things can be made watch. Then there are few this particular slide which tells that when you talk about the that injection, then from our child days we can remember that injection is a that it looks like a trauma to us. So something like very painful, and we try to avoid it, especially the children's. And think about those persons having the blood sugar high, and they are at least 3-4 times in a day they are injecting, and so how much problematic could be it is. Try to solve this problem. So can you make such be painless, and it will be easy to administer. We do not need any support power, or it will be cost effective. So this is required. It should be one of the USP is the painless delivery. I will explain you what is transdermal, because the kind of injection syringe is around 300 micron diameter, and it penetrates to the skin around say meter, and that is it reaches to the blood vein, and where in the blood vein regions you have all the sensory nerves. So that way the pain is up, and this muscular, and then even the hypodermic syringe are also the miniatures version of that, but it is it cannot avoid the pain. So here I will talk about transdermal. Length is around 500 to 600 micron length of the needle, and it is not reaching the sensory nerves, and it is diameter is so less that it will not give you any pain. And how I have learned this, I will tell you that it was purely a bio-inspired design. And actually I learned from mosquitoes, that how the mosquito sucks blood. And another USP of this product is that precise flow control. So I need how many units of insulin, how many units of particular drug, then I will insert that one in a very regulated manner with some programming. And that is connected with your cell phone, so that you can instruct your device, and as per the prescription of the doctors, you can actually dose your insulin in the body in a very accurate and precise way. So if you look at the today's problem, is a lack of choice of therapeutic device. The diseases like diabetics, offering painless, cost-effective, precise, self-administrative solution of the patient. So that we find from the survey that what we need in the transdermal drug delivery is more effective on human body for maximum drugs in comparison with oral and nasal drug delivery. So that is a recent development. Even Bharat Biotech and all these COVID pharmacy house, they are making those vaccines. They finally found that this transdermal drug delivery is more efficient, and in terms of its efficacy. And you can always say that what is transdermal? I will explain you. the skin is the biggest barrier to transdermal drug delivery. So you have to penetrate the skin, and you remain within the dermis regions. You are not penetrating further. And pain and trauma are associated with hypodermic syringes, which is one of the conventional method of drug. So most of them are actually have seen the either of drug delivery injections, and other is hypodermic syringes. The drug delivery of larger molecular drugs, for example, the insulin molecules are so how to actually give a injected in the body pressure. So we need a pump. So how to make a pump, a micro pump, so that we can push the drug inside the skin in a very regulated and precise way. For many drugs, positive volume of drugs need to be injected. Precise volume of drug needs to be injected in the body. Doses may result hazardous consequences. So that means and the repeatability of the device is very important. So mistake that even your program goes wrong, or your device, and then in spite of a precise way of dose, you have either less, the patient life will be in danger. So you have to be very careful, and the precise flow rate is required. So that will actually give you the idea how to make the micro pump, okay, MEM-space micro pump for pumping the drugs in a very precise and controlled way. And if you look at the moment, the targeted application for targeting the insulin because of the diabetic management, and so India, as you know, will be the diabetic capital of the world very soon. And statistics that what is the situation at this moment. So there are so many, and it is increasing so highly, and things, heart attacks, strokes. So all of you know all this. And if you look at the global map, so in very good positions at the moment. So so you have to take some kind of a I would say like a polio vaccine. You need some kind of delivery systems for insulin for the mass people. Even to the remotest corner of our country, we can reach, and we can actually deliver the drugs without any assistance of the medical people, a skilled power like that. Anybody can inject it, and whether we can patch like a band-aid. So such a simple way of doing the things, so that it can be adjustable. So with this background, that what is the relevance of kind of devices, especially in India, even all over the world, actually this is required. And if I look at the that the present situations, so diabetic management in the conventional approach, this is the traditional market, so needle and syringe systems, you are aware of that. And the modern market, the pen syringes and jet injectors, and those are the very expensive. So if you look at those devices, and very few companies of the world are so there's no such evaluation and a product for low cost, no low respite from the pain. So this is missing actually. So if you look at the traditional market, so still we are here. It is hypodermic, and so I believe that they are making a smart device for this kind of drug delivery, etc. So why I will go for that? So we are finding out that the what will be the market and what are the major players in it. Novo Nordisk, then Eli Lilly, Dickinson, and Hoffman Lab, etc. They are the main producer of those systems. You know, there is 14 billion market in 2020. 2025 with cumulative growth of 8.4% CAGR, and it will be 10.3% predictions for the Indian market. So global, right? It has got some relevance in the society and also relevant for the development. So this is some of the studies we need to work and to motivate today's Make in India kind of situations. Want to be very careful that whether it should be applicable and we can substitute or we innovate something to help our country. So what the patient want, we made a patient survey on it, and the least invasive, painless, self-administered, convenient, cost-effective, less risk of complications. So these are from the patient feedback. We got important points. So now coming to the so actually this design was not developed within a say 2-3 years time. So I have been working for the last say more than 10 years, and we have been I was really to see some of the early articles, and which actually me the fast striking that from the mosquito sucks blood. So if you carefully look at this, here that the mosquito heads, okay, and it is actually, this is the labium, and these are the proboscis, and this the labium portion is penetrating, and it is the head is actually vibrating at a frequency of 6 to 7 hertz. So that you can see, okay. Then I will go look into needle shape, okay. If the shape is not straight, if you look at our injections are straight, the needles are straight, edge, and then it penetrates to the skin. But have you this kind of needle? Never. But look at the screen it up in a very different, very interesting way. So understand that why nature make it that way, not straight, but this is the max out from the mosquitoes, and this is the labium. And if you look at this, the mosquitosis labium has the modulus of around 1.75 GPa and nano hardness of 0.8 GPa. So that is the hardness and the plasticity, which is actually piercing the skin. Okay, understand. The skin is to penetrate. I will give you that process you require. So the labium should not break or bend. It should penetrate to this. Okay, and apart from the labium, there are hypopharynx. So these are all having their different functionalities. I am not going into this. Okay, only I am concentrating upon the blood sucking the skin and sucks blood. Okay, so if I take this, so it looks like a bend, right? And it is around 3 to 4 millimeter, and if you look at the diameter, it's around 25 to 30 micron. And I've given you all the references. Scientific American 120, but this article that the amount for 2 minutes, the molecule of 1.9 microliter. Let me give you some interesting observation of this. First of all, blood, not water. If you look at the viscosity of the blood, is 10 viscous than water, and it injections micron. But here know that is 20 to 30 micron is the diameter. If you know the length of the tube of the channel, and if you know the flow rate, you can calculate the pressure. So how much positive pressure, negative pressure I have to create so that the blood or from sucked out from the skin. So you need to create that much of negative pressure. And you will be amazed to see my next few slides, how it is done and how actually nature created that small mosquitoes to make it. So if you look for any microfluidic engineer, and they will immediately calculate by Poisson's equations that the kind of pressure requirement is 11 kilopascal. Then I was really very amazed that 11 kilopascal, how this tiny mosquito is building up. So immediately it strikes my mind that what is there so that it creates that 11 kilopascal of pressure. And nobody can think in the world that blood can be sucked in 1.9 microliter while the diameter is 35 to 25 to 30 micron. It is impossible. So, and that is too viscous. So think of the situations at the junction, and I was just talking about the pressure. So the length is 3.8. So this is water in the blood. If you look at the diameter, so you are at the junction here. So I require actually delta P, the pressure difference required. I say around 11, so it is around 8 point something. This equations, okay? For a flow rate of 1.9 to so ability of the female pressure of the part, friction loss, etc. So because into that, there are few things that is that the meter is 35 micron, and while it's into the skin, actually in that you won't feel any kind of pain. This is number one observation. Secondly, that blood will be white while actually flowing through that. Okay, so there must be some anticoagulant which is because of right. So, nature has already done. And if you look at here, that this pressure, the female mosquitoes needed approximately 6%, and the power requirement is vibration of 6 to 7. I need some kind of a vibration, okay, and machine. So I asked one of my students that can a machine needle and and see a membrane, and from there I actually push the liquids to the needle. Then I found the pressure I require, the voltage I require is 20 volt peak to peak. Okay, and the diameter
Sorry to interrupt you.
So this is the complex situations where or 30 micron till that. And now let me explain what is the amazing science that, typically this portion is little bit of bend in nature. Now look at here, we skin needle, you may not touch the blood containing vessel. So again, look out and you have to again penetrate to the skin. That experience multiple times. If you look at it is a only movement, straight movement. But in this case, it has got both the lateral movement as well as the. So probability of getting blood containing vessel or veins will be more. Why will have this 2D kind of emotion? I would say 3D kind of emotion. So it is moving in not only in the Z direction, but also in the XY plane, because that is the way it is made like that. So that probability of encountering with the vessel containing or the vein containing blood is more in this case. So the nature is already thought of it. It is that was not of the later part. Now into there is a blood sensor. Okay, there is a blood sensor mosquito which is going along with that, and they actually position of the while it is penetrating the position of the blood containing where it actually strikes. It's not that it is like our going up and down. We are again touching it. No such. In one shot, they will blood. Have you seen that mosquito? That is the reason. So the systems have been developed in nature and if so, and those kind of amazing facts for the mosquitoes. Small create the get inspired the design of the of your systems, which is the similar kind of activity. Once I am trying to develop an and all of you know that accelerometer for measurement of acceleration, the sensitivity. That means what is the minimum g and the acceleration in outer space, and that is outer space, but it's not zero gravity. It's 10 to the power minus 6 g, even below that. So micro g to nano g kind of resolution you require for your measurement. Also, I want to get it very fast, not system response time should be much less. And all of you in the response time, they are diametrically opposite. If you want to improve the sense, you will be using its response time, because response time is proportional to the bandwidth, and the sensitivity is the k by m. So frequency equal to k by m, and what is m by k? So inverse relations. That's why you will not find the minima or the max. So you have to optimally design it. That is the optimization comes up. In the nature, What is that? I have a inner which is suspended with the compliant beams, and we are all making straight beams or spring type, meander type beams, etc. But that thing is going to help me the sensitivity and use the response time. Then I, how the kangaroo is actually jumps, response time, legs, okay. Then you will find a fantastic that the whole mass kangaroo big, but when they jump, okay, they have a very good response. Immediately they will jump. Movement through a close slow video, you will understand how these legs are made, and we try to make bridge complex beam, maybe getting and the folding, that is called folded, which can in improving the both the response time as the activity. So that is one. I'm not going to details of the design of this inertial sensor based on the kangaroo effect, but this time I am just many systems available in the world where the inspiration from the nature, and you know that my teacher is here is this mosquito who then I actually work for. It takes steps to develop at the moment. We have now the pretty kind of, so I have a little bit of idea of this. Then what is the flow and vibration? So I need some kind of a piezoelectric phenomena. So all pops up, right? Once you know that this is the way how the things should work, and in nature, then you can actually trans or the system will for a precise flow of drugs. Here, in spite of blood, I am delivering drugs into the system. So instead of negative pressure, I have to produce the positive. So then we found that if you look at the solution space, what we require, I require microneedles, definitely. And in this case, if one microneedle or arrays of microneedle, then I thought that the kind of flow rate I want, because I read the doctor's prescription, what is the unit they want, details of the design. Then one will be not good. So if we have the arrays of microneedles, a 10 by 10 matrix, so 100, okay, and they should be actuated. The lead and the second one, and the drug reservoir will be pumped by some components for a painless drug delivery system is the microneedle array, pump, and drug reservoir. So these are the three independent components needs to be integrated to give a complete systems. And I know little that how to design a microneedle and micropump based transdermal system. Okay, I am just skipping because there are one thing is pretty important, that your material choice should be such that while it is penetrating to the skin, it should, that will be dangerous. That into the skin, and when it will take it out, if in between it is skin, if it breaks, nobody will. This is a danger. Should not be fragile. So okay, and it should be biocompatible. It touches the skin and the body liquid and body fluid. So no, or kind of any sun on biocompatible. Okay. So found that hollow microneedles. So this is the microneedles. Okay. Normal, but simple, but 4 years to develop a microneedle of is around 60 micron and internal diameter is around 30 micron. An analogy that you take your hair, right? Your hair is around 80 micron diameter. Try to drill the at the of the hair to scoop a channel of 30 micron. So that is a challenge that you have to make something. Okay. Here and to reach a hollow microneedle lumen around to 40 micron size and pillar of all kind of substances. So I would say that in one go I'm not able to. Of course, another point, if you have arrays of microneedles, then all the needles should be means you need no clogging in any of the needles. That will introduce back pressure, and the back pressure will create another problem. The flow rate will be completely pumping even more, and immediately some problem will crop up. Need the yield, 100% yield, and all the needles should clear-cut path. Okay, so that is the kind of repeatability of the you require. So what I learned from this that we need not only microneedle array, that is the inner diameter of 30 to 35, outer diameter say 60 to 80 micron. So that is the whole challenge we have to make. Okay, how to fabricate that one, because any metal not seen experience seen any results 100 on titanium, but titanium is expensive and it will be a cost effective solution. I believe that something plastic polymer would have been a better choice. Let me go ahead with this low cost polymer, which is the PDMS, SU8, those are PEK, those are actually the SU8 is a good polymers for biocompatible applications. And polymers in these techniques. And here I have tried to give you some sort of a view of that, how the needles, and this is the blood veins, and where actually this is the top for the details, and the length of that is around 500 to micron. So it will never reach to the sensory nerves and also in containing veins. But what is that? It will inject to the body, then it will diffuse to the blood because this is a brick and mortar. So seepage, like through the brick and mortar, you have that how much time. So once you inject this, and then it will be okay, and then it goes to the blood. But what very recent 2021 studies, Bharat Biotech and the other over the world have found that this kind of transdermal delivery systems, the muscular one and all. So, this diffusion is there. So, not this is therapeutic. So, this is actually showing you, give you a very clear model. So, 2000 microns and subcutaneous, and this So this is all this. If you look at the skin, that is the stratum corneum, it is the top surface. It's pretty hard, you know. And I don't want to go there. So if you look at various kind of needles here, that which is penetrating also touches those sensory nerves. So that will create you the create the pain sensations. But I like to stop there. I like to stop in this. Okay, only 400 microns, so it will never touch the sensory nerves. And we have calculated, because you require this kind of data for designing your needle strength, then stratum corneum around say 1500 micron, and this is density is 1300 kg per meter cube. Then epidermis in 0.3 millimeter, so 300 micron and all these things. So, this is 9, so that is 11,000 micron. It's dermis. So if you look at the density, why I'm so interested, because while the needle will penetrate to the skin, it will give an opposing force, right? So I like to know about that. What is that opposing force? And that is the I need the maximum force. It will penetrate the skin, and once it's actually epidermis regions, you actually penetrate to the skin, then relatively it is easier to go inside, because that is much more softer if you look at from the density profile. So I need to penetrate to the skin. So the maximum pressure is required there. So my device or the needle should not be weak. Okay, the strength. So strength more, if not more, so that while it is penetrating to the skin, it should not actually break. Then I have to choose our materials. And so then we have types of drug delivery systems, microneedle, penny. So there are various kind of approaches for this. Even people talk about the nasal and oral. Transdermal is getting the best survey report in terms of its efficacy. So drug delivery systems, you might have heard about very recently the injector, but injector is painful and a huge drug stream penetrating externally and to the skin. So is quite transdermal drug delivery, but it is not that. So drug delivery system, advantage faster rate of drug delivery to define controlled drug delivery possibles. Because all of you might have an idea microneedles based drug delivery is not a new subject. But the all the developed world is basically solid microneedle having the required amount of drugs, and what it is spent is actually melt away along with the drugs. Okay, so that's the way the solid that comes up in the market. But I am not talking about solid microneedles. It's about the hollow microneedles, where actually you can control the flow of the drugs. So that's the difference from others, right? In others, they have and they have required drug. For example, I am giving some example. Suppose sugar, that you will make it and then you penetrate with the drug, it will be delivered, or some kind of a material which is glycolic acid. Those are having that nature. They will be even at body temperature inside. It will melt and very slowly the drug will diffuse out of the that mold. So these are few things that various kind of solid dissolving. So we have shown you all the kind of the solid where the research going on. So we made a detailed survey actually. Very important thing people should, what I am trying to say that with respect to that is the understand the process, the development patterns and all this. Look at that, how many papers has been published, reported. So I made it. And you can easily number of papers and the year in a particular paper and which is of the different color. For example, solid polymer, so hollow polymer, hollow steel materials. Color, if you look at it, you can find that solid polymer is now is going up, but the hollow one is the top, and then gradually you know that the solid polymer, if you look at this 2000, so you can have an idea that where is the nascent area where I can actually look upon and find this develop. So there is some development of this. So that is called hollow polymer. So you can have a pictorial view of this is up to 2018. So all these things will give you some kind of a literature survey, and if you can pictorially represent that to survey, then you and your students can understand where you are at the moment and where I have to reach. So your objective ends to be done. Where I can then you know different kind of weight because of from so SU8 is a polymer, and there are various shapes and sizes. So these are all the shapes, but none of them be 3 decades of microneedle research and PVA, these are all the materials, polymethyl, methyl, etc. Metals, normally they use nickel and the process will go for. Then the length will be 350 to 900 micron. Arrays sharp depth, hardness, biological skin insertion, flow analysis, then etc. Optimization of the process, and once you process the content. So you actually segmented all your research objective and the process and the methodology adopted in that is sequencial maker, also in a parallel. Some of them are sequentially, and there should be a closed loop. Okay, in a fab industry, we call it short run. So a short loop within 3 months time or 2 months time, will 1 month time, will get the that which will, if you change it, what will the effect. And this short loop run finally is a when you take the design and fabrication process is optimized, then you can that's why we have taken the same technique. Small studies we are doing in a parallel. So I would say the structural analysis. So one is that microneedles are penetrating, then they will get a force. And also you have to know, you have to give a force to see the bending strength of that. So both forces you have to know, maximum compressive force and also the bending force. That is important for you. So then you look at the that studies, pressure exerted by the is doing puncturing. It's 1 megapascal. That it will be more or less solid after the skin. So one here is, so we use this idea to theoretically calculate. We check out the analysis that what kind of pressure I require. So what is the flow rate? So all these things is from the insulin delivery. Microliter is 2.5. So that is the realizations. That you have to be clear that what when fluidics is for the bigger channel is in the meter or centimeter or even kilometer, for example, city water distributions. But where in case of the miniaturized micro channels or micro and you find cylindrical, then you will find that it's easy to get the laminar flow. You know that if your force and the inertial force they oppose and there will be some number, then the vortex actually here a laminar flow. So number should be less and structures. In a pipe for the local distributions, maybe 1200 to 1000, 5000. So different courses, all analysis. So those who are working in MEMS, they know very well that one is making analysis. So by mesh analysis, using various tools, we found that the stress distribution, so that maximum stress will be here and the minimal stress will be at the load end. Bending will be maximum here and bending will be almost zero at the points corresponding to the and the distribution of the stress by, and this is the meshing of the device and all this. And then we make it the analysis, the variation of von Mises stress with the outer diameter, inner diameter. So all detailed just to see that whether while it will penetrate to the skin and 80 micron or 60 micron outer layer, whether it will break or not, whether it will justify its stability and also its reliability. All kind of very extensive analysis of to do that. So we make it that under load testing, that means by micro nano indenter, we studied the actual, and we found that the this kind of needles, you saw the maximum stress might break. So better we have gone into the normal cylindrical one. Okay, so this kind of surfaces it give you much better in terms of the structure stability. Okay, so this is the stability, this is the flow rate analysis. So we found truth and all this. So what is the flow rate, what is at different diameter, and viscosity of the media change, all this has been very well. Then we found that summary. Then after all the research you have carried, you should summarize what you have achieved so far. So SU8, what is the final conclusions before you talk to your device? SU negative for suitable material for needle fabrication. Needle with simple cylindrical geometry, resistive forces encountered with the skin insertions, because we find that it's pretty high. Low von Mises stress less than SU8 yield strength. Dimension of our choice, that is length 500 micron, outer diameter 50 micron, inner radius 20 micron, diameter 40 micron. Reynolds number for the fluid is 2.1, indicating that it's laminar. Okay. The case where lumen of the microneedle is 40 micron and has penetrated micron in the skin layer, then after 600 seconds, insulin diffuses through 200 micrometer of skin uniformly. So that is the from our, there is a skin CAD model. So you can make use of the skin CAD. Really, you can picturize how the drug will diffuse in the skin and it goes from the motor structures various layer and finally reaches to the blood content. So all this can be actually visualized to that skin software, and we try to find out what is the delay actually when you insert the drugs and when it reaches the blood, how much time is required. So that time is important for insulin patient. Is not a problem. It's just like a patch. Patch and forget. So now the next question comes that, okay, I have the needle, but that is not enough. I need the conduit. Okay, so I need a reservoir below it, and after that I need a micro pump, so to push to the body. So this the whole system has to be designed. I only need the micro needle part, but what about the rest part? So let's again. So these are all fabricated data. There are few that we have observed. I am just summarizing that. using SU8. But till now, no 100 micron length, but we have been able to achieve 500 micron, and by some ways, okay, that we have picked. And then if compare that, we are satisfied with the UV, that is their ultraviolet non-way of kind of laser mask, and from there you expose it to UVL and so on, because the lumen uniform is getting disturbed. Whereas direct right, okay, where you are spinning, you use that the laser with a particular dose, and you just scan the laser on the SU8 design, then you can directly pattern your on the SU8 platform, and so it is giving much better structural. I would say it's the all the lumens within that array will remain free. There will be no and uniform. Are uniform. But in this case of direct, indirect kind of, that is under UVL exposures, you found there will be not that good. So that's the observations we found. But this W, that is a direct laser writing, I need to develop a new machine to make the fabrications batch wise. So thousands of needles will only one pattern. So just laser will scan and make that needle after. We have designed, and we are now looking, and because it is not a normal kind of a writer, but need a space writer for that. Normal mass writer can do that, but that will be expensive. So your cost of the device, if you can customize your design, and then your cost will be much lower. Okay, because I need dose of laser, and I need a certain pitch, and I need it's just routine operations, so I don't need complications and all, and I know, and so on. Very dedicated systems. Then now look at this screen very, very well. What we have done, that I need to make the needles, and the needle should have, it's called like a plumber, you know. I need to make a conduit, drug reservoir, like your tank. It will come like your tap. So it will come to the needle through a pipeline. Where is the pipe? So what we have done, you can look at this structure very well. You know, this is a needle, cross-sectional inner diameter. And then we have each silicon. This is called diverging, it's called convert, nodule shape, right? And we have aligned this needle exactly, its axis matches with the axis of that. That is a great work. It requires a lot of perfect alignment. And why I made that one diverging and converging, because will be much lower. Okay, so in this way, and in this side there will be a membrane, which will be the vibrating skin, and it is the reservoir. So the drug will flow, or you can make the reservoir here, and then the pump, then the your membrane, vibrating membrane, and it gradually it will now go with this. So that is the other side of the. So you take the wafer from this side, and here the back side, that thing. So it is the conduit. So a dive, like a nozzle, is used as my and then is the membrane. You can, if you can make it that on the sides and that cross-sectional on this. Hello. Yeah, any questions? Hello. Up to that, you can, because I don't want more from you also. Yeah, can you tell me that which point you are missing? And there are few important things that I can also replace: Pyrex glass, feather, etc. So these are all the areas. So how to make these wafers, and on the top make the needle, and at the you can actually uh, and the vessel, the drug reservoirs. So this is actual structure looks like. So after the coating of patterning, so you take a silicon 100 plane, and then you have oxidized it to SiO2 layer. Then you put negative photoresist, pattern the photoresist, then back side of the spin coated with both sides should be double polished. So now this one is back. Then you can see the patterning of this node of the other side, and then a SU8 microneedle. I will show you the SU8 microneedle for some time. So these are all the intricate design, fabrication, how the mask and all this, and the typical pitch. Okay, so 500 micron, and these are all the fabrication steps. Yeah. So you can find from the literatures my papers that they are explaining all, and then fabrication of. Then that. Then I like to share that nothing is achieved in one go. So I did not find. You will see that your lumen is blocked completely. The solid needle to fabricate is, but to make a lumen like this. So this is the hollow. It is extremely big. So change it, okay, and do it at different time and dose, and find out that where I am getting my needle. So you can see the various steps. So you can feel the lumen, and I optically I measured the lumen, so there is a block or not after some time. So repetition, this you will find finally that the structure will remain. Yeah, I got. And the other method is, I say that direct laser writing, where the laser will actually print the design on top of the SU8 layer in the scan, and then it will be much more quicker process, and the yield will be much. So we have now developing a machine for that, custom built machine. Okay. Then microneedle fabrication, laser writing, and finally we make that. You can see the structure. The DLW, the direct laser writing. If you look at that, this is the 1277 per centimeter dose. So you can find that the needle, and very clear, very clear. So This is the way different dosing. Just this is the techniques that for a laser you make it. It's called laser, so you can make it by optimal dose and the time. So these arrays are fabricated. Time it will see that in the needle, not straight, but I want straight. Lumen is there, but it is not straight. Because of we have released the structure in aqueous media. But if you have a critical point dryer, CPD, then you can have the straight wire. So that is the kind of things, but now we don't have a critical point dryer. Critical point dryer means the dry you can release. So because of the surface tension of the aqueous media, there is a bending in the structures. But this is we have seen, and how to improve that is to have a critical point dryer to release the MEM structures. And the specifications, targeted specifications, you know that one specification is your objective and another specification what you finally being able to achieve. Okay, so that is most important, which is achievable. You might get starts, but you know that sometimes it is not so easy. So you are using the structural material here is SU weight, fine, SU weight. The process we have zeroed down to direct laser writing. Length is 500 micron. And out of singular array, we are going for the array. Then the structure is straight hollow cylinders. Needle spacing 500 micron with 100 micron and lumen 40 micron. Okay. So that is our final specific nails that is possible through this fabrication technique. You understand that you have first an objective and inspiration that finally you can achieve. It has made you less 25, right? So now look at the sectional view of that. This is the this the wafer and the needle and this is on the top of that that alignment we adjusted so that you can see even from the top that this is the needle and the other side is the gap. So now we make all kind of testing indentations for the what kind of compressive stress as well as from the bending by nano indentations, and you have to do it at this surface. So this laser log. So this is the point. At this point, study 4 or 5 times to see the compressive strength. Okay, and then you EV rating. Young modulus is found to be 4.57 GPa. Hardness is 0.3 GPa, and direct laser writing it is 4.6 GPa. So more or less it is good. Okay, and you already know the hardness of the labium portion of the mosquitoes that penetrate to the skin. So it is much better than what we have achieved. So is the microneedle, there are few reported one. We have followed these literatures, that is Halholi and Exu. And another very interesting test, the actual test will be carried using chicken skin. Okay, that the chicken flesh on which by nano indenter we are penetrating to the skin, to the needle, and they different diameter, what is the indentation depth and the indentation. So if the load increases, how the indentation depth will change. So definitely if it's the breaking point. So that signify that the skin is punctured, that it drops because the against force will be reduced because the semi-solid. So here is this. And definitely that will be the lowest diameter, mid diameter, say 200 micron and 900. The higher the diameter, your resting force is much higher. And so that is the way how the skin can be actual. You can do it on the strengths. Okay, and then the characterizations. Let me tell you that when you cannot do this kind of a special thing. So you have to you have two places. So you can see one is that this is the edge, which actually to the top of the needle. So that is for compressive stress, and where this one put it in a vertical view, so that it will give you the lateral stress. So you find out the bending moment of that. So you cannot do it in a normal micro or nano indenter. You have so we made that special jigs and arranged that one. We made these measurements in IIT Hyderabad. Now coming to the actual efficacy of that. So we have now water pressure. So pressurized water. And now the first test is the light test. Very simple. You put your sample, and from the below you shine light, see that light is coming uniformly or not. So this is your is coming very uniformly. And other one is that the actual flow. So we actually connected with a inlet with a water and find this is a stream of water coming out of the needle. So it's a very straight. So that means all my lumens are open. And also I found what is the flow rate and the pressure. So this is the inlet pressure and what is the flow rate. This is in the microliter. So it is, say, I give 4 kilopascal, 2 kilopascal. So what is the flow rate? So I know that what kind of pressure to reach certain kind of flow rate. Okay. So this is the after that make this next most important things. You are going to make the device for skin, and there are various stages of its adaptable, means acceptability test. So first you have to test with the animal. So you know that the mouse skin and the rat skin are very close to human skin. So we have chosen both mouse, a particular kind of mouse, and the particular kind of rat, and we put at different places of this the patch, and we see that what kind of and you before you do any biomedical testing, the supervision of the CPCACA, that is, there is ethical committee clearance. So you should have the ethical clearance. What, how many will be sacrificed, and so on. So, and detailed protocol has to be registered there. So committee will decide all the protocol which is obeying the international protocol or not. And once you get that license, then and only you can make all these measurements. So we got that license from the CPCAC, which is in the government, and measured it accordingly, according to the standard. Skin, we are trying to find out after penetration and penetrations various times whether my then we found no such breaking events. And after seeing that, we see that something remains within that. I say nothing. Looking at the patch, how it looks like that, and keeping that for 30 days, toxicity or there is any kind of a reactions over, not fine. Then he found this blue colored dye as he penetrated, and see that how the drug diffuses inside the skin of this mouse. So we'll sacrifice that, unfortunately, and see that whether it is good. So it is preclinical trial, okay? So on the mouse, and so after that, if you look at the hollow microneedle, that inner diameter theoretically calculated was micron, then characterization results is 30 micron, outer diameter 100 is 112 micron, length 500 micron to 500. This is the average length. Structural materials SU8, DLW. So you have to supply all this. When you something you design for productization, then all this thing you have to make all the documents in a very, very a way, methodically you have to. So finally what you require, so this is the form, okay, Reynolds number and everything, you have to give those data for the needle structures. So the summary, that a MEMS-based novel technique of 8 microneedle with an aspect ratio of 5 conduits on silicon substrate successfully made, and so on. So now we'll go to the pump side. So before that, I like to have interactions with all of you. So first of all, how do you like? And if there is any questions or if any kind of doubt anywhere, you can.
Now the floor is open to questions. So if you want to ask sir anything on the topic, you may please ask.
Yeah, so this is not the end of my talk, so I will continue. But up to this hollow microneedle and its integration, I will go to the pump now. If any question, because it's a very big. So if not, the actually, I should give you some kind of a feeling. Let me see. Can you see my screen?
Yes, sir, we can see the Zimra. I think
You can see
have
my
opened.
screen, right? Yeah.
Yes, sir.
Yeah,
We can see Zimra. You're opening probably your email server. Yes, sir. We can see.
I think all is, there's no such visual. So now this is the right time to give you a visual. I'm very sure about the very slow. Okay. So this is a documentary on my work. And let me just and it is a 1 hour documentary, so I will give you 5 minutes exposure to that, where particularly new my God, why? think of to just connect.
Hello,
Start.
sir. Uh, sir,
Yes.
I think there is a problem with network. So we can play this video from our system, if you allow. Hello, sir. I think there is a network problem. So if you allow, we can play this video from our system. Hello, sir. Can you hear me?
I think, Sumi, there is some connectivity issue probably. So
Yes, sir.
let us wait.
Hello, sir. Can you hear me?
Yes, Sumit, I think sir has joined again.
Yes,
So
sir.
let us see. Sir, can you hear us?
Participants, please wait for a few minutes. Resolving the issue.
Hello. Hello, can you hear me?
Yes, sir.
Yes, sir.
Yes,
So,
sir. We can hear you.
what's my voice? Okay.
It's clear
So,
now,
can
sir.
I continue? Uh,
Sir, actually, we
should
have
I
the video. If you allow, we can play from here. Hello, sir.
after that
Hello.
I talk some? Listen to that. Hello.
Uh, yes, sir. Actually, we are saying we have the video, sir. We can play from here if you allow us. Hello, sir.
Play, but I am not to save time. So because to YouTube, so find that there are several such video on this particular work. So can you see the PPTs now?
Sir, till
Can
now
you
not.
see?
No, sir, till now not. So, please
You are
share.
seeing still the okay. So share. Oh, still here. No, I am not going to. How to cut it? I don't want to share this. I want to share this. Yeah, can
Sir,
you now
that's
PPT?
sir, till now not, sir.
Hello.
Hello, sir. We are unable to see your PPT, sir.
Then what to do? The documentary here still thing. Can
Sir,
anything?
sir, please share your PPTs because documentary is they are taking
Yeah, because I
more
am sharing
bandwidth.
it. You see.
Sir, not, sir. Please
I'm sharing it.
stop.
Uh,
Sir, you can try.
oh my God, it is gone. Yeah. So, can you share? Hello.
Yes, sir.
Can you can you see that?
No, sir. It is showing only to
Hello.
you are trying to share the. Yes, sir. Please, sir, start sharing again, please, because I think you have stopped the sharing.
No, I am doing it. Just 1 minute. This is the screen. So I share the content. I'm sharing. You can see it now. You can see something, na?
No, sir, we cannot see anything.
Okay, share. Okay, 1 minute. Share. Can you see anything?
Yes, sir. You have yes, sir. We can see your screen now.
Now,
Yes, sir. We can see your screen.
if it is. Okay. Have you heard about the glassy carbon part?
Yes, sir. Actually, please, sir.
Yeah.
We are able to.
The glassy carbon, you have seen paper and everything.
Yes, sir.
So let me, very interesting applications what have been developed from my group is the micro pump, a micro thruster, and micro valve for nano satellite and pico satellite. All of you know that the India is launching 124 satellites in one go, but those satellites are known as the pico satellite or nano satellite. Its weight is less than 10 kg. Now, while these satellites is orbiting around the Earth at a particular orbit, then there is a problem. The problem is, although we say that the gravity of the Earth is outside the Earth is zero, but it's not zero. There is a micro g, or out of that acceleration, so this satellite away. And so the transponder will actually, in spite of beaming to India, to the to ocean or other country. So the exact parking lot, they should remain at that orientation of the satellites. And how it is done, now, first of all, they give, I have developed this for ISRO long back. So we call it a MEM satellites. So, hello, the whole idea is that you have to first, you have to check the acceleration there and not any data, because the acceleration is so less, so get any kind of appreciable data in these systems. So you need to have some new technique for acceleration, and that is called the micro accelerometers or nano G accelerometers. Quantum tunneling phenomena of electron. So when it is integrated into the accelerometer part, so it is a combined project given to me, challenge sensing and actuations. So it will accelerations, and accordingly, the thruster will be actuated, and first it will realize the movement of the satellite. That is the whole idea. The time is less. So let me go into the details of that. There is of the propellant impulse. What is the total impulse? It will specific impulse of that. Out of that, you can grade various kind of propellant. So there are hydrogen, there are hydrogen peroxide, there is water, there is different kind of propellant about the liquid propellant. But in civilian applications, we are using the simple water, the concepts. And then it was tested in ISRO, Indian Space Research, to work with the actual hydrazine that is the propellant. So I'm going to structure. So there are two things. One, this is the inlet nozzle, the water from the valve, and it 1 kilopascal pressure it is going through this we call cavity, and that cavity is fitted with. So this heating, the micro heater will heat it up to the supersaturated 20 degrees centigrade. Water will vaporize, then there is divergent convergent, and there it will actually pass through that jet, the water vapor, and at a minutes or max 3 minutes, 3 times of the, and that will introduce sufficient pressure or thrust or opposing force so that the satellite will remain in its position. It will not drift away. So we developed that. We made So the nano and the year of service should be at 5 years. Mind you, is launched for 5 years. Actual life is for 10 years. So we have to design our space-grade devices in years lifetime. Then they will declare that it will work for 5 years. So now the things that these are all the and all this, how to make, and so details of the micrometer, how to under temperature, what is the requirement, doping, so how it will look like. This is the so these are boron diffuse heater, and we applied voltage across it, so it is heating. And you know that silicon and silicon dioxide doesn't matter. You microseconds you will find that the temperature from the whole it reaches. So in the cavity is basically heated by the heater which is back of it. Previous test and all this. So finally we checked it, the heating performance. Now we are going into the that again the fabrication is coming. This is these are all, now you can find this micro nozzle, the actual picture of the micro. So water is fed, then the micro heater is heating it, and then the jet is fitted with the satellite so that it arrested motions. And this is the inner view of that. So after that testing, this is the bonding, the thrust. Okay, so the top wafer bonded it, and we take this away along the XY plane. So these are all. We made a simple arrangement, a copper and with a mirror, and there you can actually flow the water at a very small, and that droplets will actually goes inside and heated up, and the thrust on the disk, and it will move up, and there is a laser beam. We can find out the displacement and so on. So that is how to establish the thrust. And secondly, we made our design to measure the thrust by the weighing machine. We have actually made the thrusters, and then correspondingly we are making from the display, that is it is two kind of force or thrust. The thrust of 120 micronewton to 1.2 millinewton. So sorry, 400 micronewton to, that is good enough force for checking of the micro or pico satellites. So after achieving this one, then we found that each requires 3.4 microwatts of power, and the backup in the satellite will mean which has lifetime of the 10 years. The ISRO given me a task that whether you can make a device energy harvesting that do not require any kind of but automatically it will generate the power to evaporate the water and give the required amount of thrust. So to save the battery, to increase the battery life, I took up this challenge, and then we found a very interesting observations of this. So what we have done, that in of this micro heater, we replaced with the manganese MnO2 nanowires, oxide nanowires, which is actually in the nanostructures levels, and which is in spite of actually placed glue in these regions. Okay, and the H2O2, hydrogen peroxide, and 40% and 40% is water. While it goes through that, then what it does that they improve the flow of the hydrogen peroxide and temperature of 120 degrees centigrade. So it takes to the H2O and oxygen, so that hydrogen that is which is coming out of this H2O2 is immediately reactions. So you do not need any battery operated microheater, but because of the microheater is a very controlled cavity reaction, chemical reactions, you introduce that temperatures and it's good enough for making the vapor. And the vapor goes from the of thrust. So we have tested the structure, its morphology, and so on. But it's a catalytic reaction. So MnO2 is not reacting with the H2O2. So even 1000 cycles, MnO2 H2O2 breaks and is an exothermic reaction, and this chemical reactions gets excited, gets stimulated from the MnO2. So that's why I can have this confined reactions, and then you can some kind of energy harvesting approach where I can actually develop this kind of thrusters. So here we can see, if you look at the thrust, so I can go from say 100 micronewton to 1.2 billion newton. So that meets my specific. Okay, so that is another very good examples of this for the satellite. So I gave you two extreme examples that this is the MnO2 nanowires how dispersed over the cavity without the microheater and so on. 10 to H2O2, so fine. So then after that, this is not yet reported, there is a carbon nanotube decorated with iridium can also give the same phenomenon. Okay, so that is the carbon is coming up. Black dots, this is iridium particles, and that also gives you the same catalyst copper. So you can make use of this CNT iridium, and to make, and we can found a similar kind of this vaporized liquid, and it provides me the required thrust to arrest the satellite, keep in the same positions. So I can. So I gave you the on how to make the painless microneedle or the about waiting for the human trial for finally it will go to the market. Is this technology that we have developed is a MEM satellite, which is for microvalve and micro reservoirs. This has also been taken by batch fabrications to SCL. So total technology has been transferred to ICL Semiconductor Complex Limited. So there we are using this. I think that I should stop now, and if there is any questions, you better. Okay, these are the references. Okay, thank you all. So there are things in my experience, but I shared only a very few. If you look at my recent publications, I'm mainly now focusing on the area of nano biosensors. So in another occasions, introduce the bioscience together for various applications, air and water pollution measure and control. And if you miss something, you get it in my video. So you can find all my work. And also, if you look at my papers, you will find all this work.
Thank you,
I'm
sir.
stopping now and is now open for questions. If you have
Thank you, sir.
questions,
Participant.
you can ask me.
Thank you so much, sir, for the nice and informative talk. So even though there is some minor, disruption in the network, but we could understand many things. And also we'll be providing all our participants with the YouTube video that you tried to share.
Yeah.
But to connectivity, it was not played. So we'll share with your kind permission and approval. We'll be sharing with the participants if you kindly allow, sir.
So that
The
documentary
YouTube
is
link.
open to the public. It is available in YouTube.
Yes, sir. Yes,
Where
sir.
all my research, glimpses of my research, you will find from that documentary. It's a 1-hour documentary. So my research in other areas.
Yes, sir. Thank you so much, sir. So we have already shared the link with the participants. Now I'll be requesting the participants, if you have any questions to sir, you may please ask.
Yeah. They are hungry now.
Yes, sir. So, sir, I guess all the audiences are humble enough not to ask any questions. Yes, sir. So, sir, thank you so much, sir, for sparing your valuable
Question.
time with us. And
Anyway.
thank you so much for sharing your experience with us. Thank you, sir.
Thank you very much.
Yes, sir. You please have a wonderful day, sir.
Bye-bye.
Bye, sir. Bye.
Good afternoon, everyone. So I welcome you all in the ninth session of AICTE sponsored ATAL Faculty Development Program. This session will be delivered by Mr. Chandravan Patel. He is a PhD student in the HNRG group. The topic of the session will be 2D TMD materials for next generation portable biosensors. So now I request Mr. Chandravan Patel to share his slides and continue with the presentation.
Thank you very much, Sumit. First of all, I want to thank Dr. Shaibal Mukherjee because he has given me this wonderful opportunity to present this work. Recently, we have started this work related to the 2D materials. So, in the start of my talk, first I'll focus on the deposition of 2D TMD material via CVD because it is a very crucial part for the other applications, and it is very important uh, to design portable sensor and other related applications of 2D TMD. So first we will focus about the deposition of 2D TMD materials. So I am sharing my screen. So Sumit, my screen is visible for?
Yes, and you can also switch on your video.
Okay. So now here, first I'll give the brief introduction about the different application of 2D TMD materials for various applications. After that, I'll start the complete video from precursors to how we will transfer it from other substrate TMD material. We will try to cover the whole process in a single video lecture or in this lecture. Okay, so in the motivation parts, as we are very well known of these facts, many diseases are directly correlated with the environmental pollutions. So many toxic gases are present in our pollutions, and as the threshold limit of these gases increased, so these are very toxic for the human being. So as I have depicted in the picture, how they are harmful for human being, and here in the right hand side of this PPT, I have mentioned the different application of TMD materials for different applications. Here, gas sensors, which will I'll focus in this lecture, and other application is also here: energy storage, electronic devices, biosensors, piezoelectric devices, and photonic devices. So these are other applications, but mainly I'll talk about the gas sensor application in this particular lecture. So why we are focusing about TMD materials for gas sensor application? So this is a basic question to start this presentation, because when you will go through the literature, most of the studies for gas sensors related to metal oxide based sensors, you will find it. But what is the major limitation with metal oxide is that higher operating temperature, and another limitation with the metal oxide is that uh, lower selectivity or poor selectivity. These are the two major limitations with metal oxide based sensors. So that's why researchers now have focused on 2D TMD material for gas sensing applications. And what are the advantages of 2D TMD material for gas sensing application? So first, it works at room temperature. So it will overcome the requirement of any heater device or any higher temperature operating temperature. Second, major importance of the 2D TMD material in gas sensor, it has very high surface to volume ratio. which makes very important for sensing applications. So these are the major two advantages of TMD material for gas sensing applications. Now, so sorry. Yeah. So here is the CBD schematic because we are using 12 heating zone CBD schematic, and each heating zone is independently controlled by we can control independently. It means if we are heating a particular zone 1, so it will not affect zone 2. So because as you can see in the schematic also, 3 centimeter insulation zone between two heating zone is provided in the CBD. So we are using 12 heating zone CBD schematic CBD, and it is automatic. It is not manually operated. It is fully automatic CBD. So we provide the recipe for the CBD. Recipe, it means particular growth directions, in which particular growth conditions or directions we provide the CBD, and it operate automatically. Here I am using the term recipe. When you will go through the literature and for TMD materials, so you will find this term generally, and you will go through this term recipe. Why I am using recipe term here? Because when we we can also correlate with the food recipe or other recipe, because when we prepare a food in our home, so generally there are two things. First, quantity, and second thing is quality. So it's these two parameters or characteristics of food to mainly depend on the ingredients. What type of ingredients we have used during the process. So that's why similar here we can also correlate here. Here your film we are depositing TMD material. So your material length or your material size, uniformity, all these things. First, the quantity means number of how much size it has deposited. It will depend on the certain ingredient during the process or certain precursors. And second, quality. It will also depend in another parameters of this process. So here is also the two things. First, the quality and quantity, and second one is the quality of the material. So in this video lecture, we will also understand how we will identify the quantity of the material we have deposited and how quality of the material. So we will also talk about the certain characterization technique also. How we will evaluate actually how much how we will evaluate it has deposited in this particular area, and which type of quality we have obtained during this process. So now I'm sharing the video first. So it will, I think, because these are the just schematic here. So video will give you the more knowledge or more information about the CBD systems or deposition of TMD material via CBD. And another thing I want to request to all the joinees, if you have any doubt at any stage, you can ask me because you can feel free to ask any question. Okay. So now so now I am playing a one video which consists. Sumit, can you see this video? Sumit?
Yes, we can see.
Yeah. So this is a CBD system. It is in our lab, HNRG lab, guided by Dr. Shaibal Mukherjee, Professor Shaibal Mukherjee. So here in the back of the CBD, in this diagram, I'm just pausing for a while because I'll mention each and everything, because I didn't actually give the here heading any particular thing because it will be very complex. So I am explaining simultaneously what are these things. So here you will find that these are the actually thermocouples. As I have already mentioned that this CVD system consists 12 heating zones. So here in the back of the CVD, you will find that here are 12 thermocouples are associated with it. So it means each thermocouple is associated with each heating zone, which will measure the temperature for a particular heating zone. So these are the thermocouples for individual heating load. So now this is the front part of our CVD system. So these are the front part. Here they have given the scale actually. Why they have provided this scale here? It will actually measure the our tube dimensions, tube length. So that's why they have mentioned here the tube dimension. Another thing from the scale we can measure it when we will place the alumina boards inside the tube, quartz tube. So we can measure that distance between these two boards. So that's why they have given the scale here. And this is the front end of our CVD system, which consists the MFC unit controller, power controller unit. All these controlling units are here inside the CVD system. Now at the right hand side of this CVD system, once monitor screen is also associated with this system to regulate or operate this CVD system. Here at the right hand side on the ground you will find it. Here is the vacuum pump. Vacuum pump is placed there beside the CVD system, which will generally use to make a high vacuum in the quartz tube before growth or before starting the any recipe in the system. So that's why here is the vacuum pump is placed beside the CVD. And here you will find it. It is in a actually find it there is a bucket is also there, and in the bucket we have actually dipped a one coil is there. So someone may ask why they have placed the bucket beside the CVD. In this bucket, when you will see this here, what you will find that this coil is dipped or immersed into the water. We have filled the water in the bucket and we have dipped the coil. Why we have done this thing? Because generally we are using this CVD system for deposition of MOS2. And as you know, we are depositing MOS2. So MO, molybdenum, and sulfur will be the precursor. In that case, what will happen? Sulfur will somewhere will be condensed there. So it will maybe deposited on the quartz tube. It may be on the stainless steel pipes or polypyrylene pipes. These are yellow color pipes. So what will happen sometimes after some runs or many runs, what will happen? These pipes will actually choke, you can say, or gases will not pass through these pipes. So what we generally do, we have done these things. We have dipped this coil in the bucket. So what will happen? Sulfur actually will not condense at the hot in the, you can say, the higher temperature range. It will condense in the cooler zone. So what we do, generally we mix the ice in the bucket. So sulfur will condense here, not in the polypyrylene pipe or stainless steel pipe or in the quartz tube. So to remove the sulfur condensation, we have generally used these techniques. So before starting the recipe, what we do generally, we fill this bucket with water and put a certain ice in the bucket. Okay. And now here you can see this yellow valve is here. When you will find this yellow valve, this is actually manual purge valve. Generally we call it is manual purge valve. Why we have provided this here? Similar to exhaust the sulfur. When we will clean this quartz tube, we have required to provide the path for a sulfur, for an exhaust actually. So that's why we have provided here the manual valve is here. So using this pipe or using this valve, SO2 will pass during the cleaning process of the quartz tube. And here, this stainless steel part, as you are seeing on the screen, this is actually called as the right hand vacuum assembly. This is whole part, whole stainless steel body, as you are seeing on the screen. This is the right hand vacuum assembly. What it is do, similar type of vacuum assembly is also associated on the left hand side. So in this CVD system, two types actually, right hand vacuum assembly and left hand vacuum assembly. These both vacuum assemblies are associated with the quartz tube. So quartz tube inside the CVD system is associated with these two. So from the one end, we will insert the gases in the quartz tube, and from the other end, gases will come out. So this is the right-hand side vacuum assembly for output side, or you can say the exhaust side, exhaust end. Here you will see this butterfly valve, this black type valve, open and close, as you can see on the screen. So it is connected this to the vacuum pump. So when we open the vacuum pump, simultaneously we open this valve. So high vacuum will create inside the quartz tube. When we close the vacuum pump, or we turn off the vacuum pump, simultaneously we close this vacuum valve. So this black valve is generally we called as a butterfly valve. And in the this right hand vacuum assembly, at the top of this, as you are seeing, there is another valve that is called release valve. Because in certain cases, what will happen when your this manual purge valve has choked in some condition? So this release valve is for only safety purpose. If because in this system, in this CVD systems, are actually 3 valves are there for to exhaust purpose. First, this is a manual purge valve is there. At the back end of the CVD, you will find that there is a actually solenoid valve is there, and this release valve. So if in some cases, or in some accidental cases, if what happens, if these two valves are closed and are not actually passing the gas through these two valves, so you can open the release valve. So your tube pressure will release it. So this is a safety valve actually. So these are the, yeah. So now you can see on the screen, on the below of these all polypyrene pipes, you will find there is a solenoid valves. Because as you can see on the screen, one yellow color pipe is also attached with the solenoid valves. So there is the solenoid valve. Yeah, now you can see clearly on the screen. So when it will open and how it will work, as we are very well aware of the fact that it is just as its name suggests, it is a solenoid valve. So we have provided, it will work as a switch. When our quartz tube pressure more than 100 millibar, then this solenoid valve will open automatically. We will not have to do anything. Simply this valve will system will give a command to this solenoid valve, and it will this valve will open automatically. So the tube pressure will release using this valve. So this is also a safety purpose. So it will also alert us, yeah, our tube pressure is going to rise. Now, these are the cylinders with 99.99% accuracy. We have purchased from AGM, air gas material. So these are the 2 cylinders, as you can see here. So one cylinder is oxygen cylinder is here. Another cylinder is for argon gas. So these 2 cylinders are placed here. And these 2 cylinders are connected via MFC into the input port of the CVD. Now you will find that here is the MCB. It is a 40 ampere MCB. So it will provide the AC supply for our system to work it. So this is a 40 ampere MCB is connected here. So now, so this is the actually basic setup. I have just explained it about the CVD system. But before opening the lid, before opening the lid of a CVD, or before explaining the other parameters, how we will place the alumina boards inside the quartz tube, other things, how we will start the CVD, what type of temperature profile, carrier gas flow rate profile, and other things. Before, what we will do, we will first prepare the substrate, because we will have to place the substrate in one alumina board. In another alumina board, we will have to place the precursors. So first, I'll explain the cleaning procedure for a substrate. In this recipe, or in this process, I am using SiO2 coated Si substrate, 300 nanometer SiO2 coated Si substrate. So first I'll explain the cleaning procedure of a SiO2 coated Si substrate. Here, as you can see, I have actually in this video I didn't show the wafer cutting here, because it will make otherwise this video will take much more time. So I have cut the silicon wafer by a diamond cutter in a desired dimensions of the samples which I have required. So what is the dimensions I have taken for the sample? In this, I have taken 2.5 centimeter length for the substrate and 1 centimeter width of the substrate. So now I am dipping the substrate first in acetone for cleaning, and now after that I'll sonicate it for 15 minutes. So one by one, I'll start the sonicator, and I have dipped in acetone. It will take 15 minutes, and after cleaning in acetone, next I'll dip into the TC IPA subsequently and clean one by one for 15 minutes. So what will happen? Organic impurities and other impurities will remove from the SiO2 Si substrate. Why it is required to clean it before placing the substrate? Can we place the bare substrate or before without cleaning the substrate directly into the CVD? What will happen if particular contamination is on the surface? So it will actually it will stop the growth of MOS2, because MOS2 growth generally favorable on clean surface and very smooth surface. That's why cleaning is much more necessary and it is much more required. When you will go through the literature, you will find the paper, they have mainly emphasized the cleaning procedure, and they have talked about in a very much depth how the importance of cleaning of substrate in MOS2 growth. So that's why cleaning is very much required before growth. And so this is actually sonication process. So it will remove all the organic impurities and other impurities from the substrate surface. Now I have dipped in IPA. So similar, after that, at last, I'll dip into the DI water, or we can rinse it in DI water also. And in the last step, what we will do, because some water molecules or water drops are left on the substrate surface, to remove these water drops from the substrate surface, what we will do, we will purge it. Now we will purge it, the substrate to remove these water drops from the substrate surface before placing these alumina boards. These are the alumina boards, white in a white color, as you can see. So now I'll purge these. Someone may ask why I have taken these two substrate here, or two SiO2 Si substrate are here, because when you will go through the literature related to the MOS2, you will find many methods for deposit MOS2, and as you are you are using first time synthesis of MOS2. So according to your knowledge, you will have to choose which particular method is most suitable according to your application and other parameters. So here I didn't directly evaporated the MO and sulfur powder. I have coated the MO powder onto the one SiO2 Si substrate and another SiO2 Si substrate as taken as a bare substrate for MOS2 deposition. So that's why I have taken two SiO2 Si substrate here. I think you have understand this particular point. I didn't take MO directly. I have deposited MO1 first substrate, and another substrate I have used for MOS2 deposition. In this video, you will understand it. As we will proceed, you will understand it, each and everything. If further, if you have any doubt, you can ask me. So now what I am saying, we will have to remove these water drops from the substrate surface. So we will purge it. Yeah. So inert gas, we have used nitrogen here, and now we will purge it. So we will have to hold this substrate gently here, because if you are not holding properly this substrate, what will happen when you will purge it by this gun? What will happen using the press? Nitrogen pressure is here, because you will apply a gas pressure on the substrate surface. So this substrate may be through from your hand. So you will have to hold gently, not very much force. Otherwise, what will happen? Substrate may will break or damaged. So you will have to hold this substrate very gently, and you will apply a gas pressure on the substrate surface to remove the water molecules from the substrate surface. Yeah. So generally, when you will purge it, so you will hold this substrate and you will apply a gas pressure from the edges of the substrate. What will happen in that case? What will happen? Not directly on the substrate surface, from the edges of the substrate. So these water molecules and other things will remove easily. So that's why I'm holding this type. So this is another thing. Yeah. Now we will do the same for another substrate. So this is the actually cleaning procedure for our substrate before using the growth. Yeah. So now we have cleaned the both substrate. Now I'll use the spin coater. This is a spin coater. Why we are using spin coating here? As I have mentioned that I am not using directly MO powder. What I'll do, I'll coat the MO on first substrate. I'm not using the MO powder directly in the CVD system. I'm mentioning this parameter repeatedly at this particular point repeatedly. Why I'm mentioning it? Because powder evaporation, we can't control the powder evaporation rate very accurately. That's why I am not placing the MO powder directly in the CVD. That's why what I am doing, I am dissolving MO in a particular solutions. As I am for your information, I am mentioning here, MO doesn't dissolve in DI water. So I am dissolving MO in ammonium hydroxide. After that, I'll coat it on SiO2 Si substrate. So I have also mentioned the reason here, because we can't control the powder evaporation rate efficiently in the CVD system. That's why I am using solution process method here. Okay. So now we will coat the MO solution onto the SiO2 Si substrate. So this is a spin coater. We will set the, because it is also programmable. So first we will make a program at how much RPM it will rotate and for what time actually we want to run it. So we will set a program according to that, and we will first, if you are using spin coater after 2 to 3 months or 3 to 4 months, first what you will do, you will warm up. Warm up, it means it will, when you will warm up this spin coater, so it will reach the highest rotation speed it has actually. After that, what you will do, I'm not also calibrating here because I have already calibrated it. So just simply I loaded the program, which I have already made it in the spin coater, or I have loaded in the spin coater. In the calibration process, what you actually, when you will use the different substrate, then the calibration will be required, because your substrate is held by vacuum, certain vacuum there. So if you are using sapphire substrate or SiO2 Si substrate or other substrate, is a aluminum foil, copper foil, gold foil, so your substrate dimensions and substrate weight will be different. Then in that case, you will have to calibrate the instrument first. So your spin coater will understand that, yeah, this much particular weight I have to hold it. So how much actually vacuum I'll have to create or required to hold this substrate properly. So that's why I have already done this thing. So that's why I'm not calibrating here. Simply I'm loading the program, which I have already stored in the spin coater. So by pressing the second key, second number, I load the program and I'll place the substrate here. Now you can see on the screen. So this is the SiO2 Si substrate I have placed on the sample holder, and after placing, I'll press the vacuum button on. This vacuum key is there also there. So now what will happen? Vacuum pump will associate on vacuum pump, on a small vacuum pump will also associate with this spin coater, so that we will have to on first. After that, we will press that key, so our sample will hold properly. So now it has green. It means vacuum has created there, and our sample are hold properly. So when it will rotate the sample holder, our substrate will not throw. Otherwise, what will happen if it is not hold properly? When it will rotate at a 3000 RPM or 3500 RPM, substrate will throw from the sample holder. So we will have to keep this point in our mind before placing the substrate into the spin coater. Now, what we will do, we will we will drop MO3 solution on top of the SiO2 Si substrate. This process is called as MO3 coating on the SiO2 Si substrate. So now it has we will wait to reach the at higher speed which we have programmed in our program, and after that we will coat it, because it will take certain time, because that time is called acceleration time, as you can see on the screen. So we will have to, when we are making a program for a spin coater, we will have to provide the sufficient acceleration time according to your RPM, at what RPM you are going to use it. So we'll have to provide the acceleration time according to that. Now it has reached the speed at that final RPM which we have required. Now we will try to coat it. Yeah. So we have used a micropipette. As you can see on my hand, I have taken the 10 mul micropipette. What is the capacity of the micropipette? I am using it 10 microliter. So now I'll coat this, and I'll drop it gently on the substrate surface. When you are dropping it, please wear one face mask and glass also, because when you will drop on the substrate surface, it may one water molecule may throw, so it may toxic for your eyes or something. So that's why please wear a mask or certain component. Yeah, so as I am showing it, at what particular scale I have set in a micropipette. Now it will, as the time has completed, it will stop it. And first what we will do, we will stop the vacuum. Yeah, so we have removed the vacuum. Now we will take our substrate from the sample holder. Yeah, so, and we will place it in particular alumina board. We can place in another any alumina boards. It is not required to place in this or that one, because both are same. Yeah, so now we are placing this MO3 coated SiO2 Si substrate in the bottom of the alumina. So this is a interesting thing, and the positioning of the MO3 coated SiO2 Si substrate is also important in the alumina. So we have placed it at the bottom of the alumina. Yeah, now we will take another substrate, which is a bare substrate, which is a bare substrate, and we will place it on the top of that. Yeah, so here we have, as you can see on the screen, we have placed it directly on the top of the MO3 coated SiO2 Si substrate. So someone may ask, can we place it on the left hand side of this substrate or on the right hand side of the substrate, and why we are placing on the at the middle of the aluminum? So these are the, when you will find the go through the literature, you will find these papers and papers title generally related to this substrate positioning. You will find it there. So they have optimized the distance, and they have reported the distance, what is the actually optimum position for placing the substrate in an aluminum. So in this case, I am just placing the bare substrate on the top of that. What when you will go through the literature, you will find that in some papers they have mentioned that this distance, this bare substrate, they have placed before the bottom substrate, or how much centimeter away from the bottom substrate, in the 1 centimeter. So they have find that that is the actually optimum distance. They have mentioned that in some papers. But this placement is also depend according to your application and according to your growth conditions. So it will vary, and according to your tube dimensions, quartz tube dimensions. Okay. So now what I am doing, I have placed the substrate in on alumina boards. Now we have required precursor. In a precursor, we are going to deposit MOS2. So we have required two precursor, MO and sulfur. So as I have already explained it, we have deposited MO and SiO2 Si substrate. Then in the next we have required sulfur. So we are taking sulfur. How much amount of a sulfur we will take it? It's also depend on according to your recipe or according to your application, according to your tube dimensions. So now in another alumina board, we are taking sulfur powder. So first by weighing machine, we will calibrate it or this weight of alumina board and it will come to 0. Now we will take the certain amount of sulfur in alumina boards. So it is also toxic. So please do carefully when you will take the sulfur and other things. When we are taking sulfur, so we will actually disperse the sulfur on the alumina board properly. So what will happen? So evaporation rate generally this consideration will consider when we doing the growth, because what we have required actually, we have required the constant evaporation rate of a sulfur also. So that's why we have dispersed properly in the alumina on the bottom of the alumina board sulfur. We will not make a actually we can say no, not in a one place. Simply we will disperse it properly, but we will not as it has possible according to your. So now, as you can see on the screen, we have taken both precursors. We have taken substrate. We have taken both precursor, MO and sulfur. Now we will open the lid for CVD. Before opening the lid of a CVD, we will check all these things. We have oxygen cylinders in oxygen and argon. All other things are available there. Okay, before starting the recipe. Now we will open the lid. Yeah, so here as you can see, here is the one quartz tube. As I have mentioned that it is a 12 heating zone CVD. So on the top of the lid, as you are seeing, as you can see on the screen, here are actually 12 coils are there, which will heat the particular heating zone. And on the when you will look at on the quartz tubes towards quartz tube, what you will find that there is a actually black cap is type is depicted there. That is thermocouple. Each thermocouple, I have already mentioned that in the backhand side, each thermocouple will associate with each heating zone. So these are the black is thermocouple actually for each heating zone. So this CVD consists 12 heating zone. Now, as I have already mentioned that it has a left-hand vacuum assembly, right-hand vacuum assembly. Now I think now you can see clearly on the screen. So these are these blacks actually in the each heating zone. So these are the thermocouples, and these coils are actually these are coils. So okay, now this is the actually left-hand vacuum assembly I have talked about. Okay, so this is a left-hand vacuum assembly, and this is a right-hand vacuum assembly. So both we can open according to our choice which particular alumina board we will load it. So first we I am opening the from the right hand side, and this opening of the right hand vacuum assembly will also do in a very gentle way. Otherwise, what will happen? Your quartz tube may damage. So that's why properly. Yeah, now we have opened this here, and we will keep it away from the CVD. And now we will load the one alumina board, which consists both substrate. One MO3 coated substrate on the bottom of the alumina boards, and another substrate is bare substrate, SiO2 Si substrate. Yeah, so this actually direction, as you can see on the screen, I am loading the SiO2 Si substrate and MO3 coated SiO2 Si substrate these are actually because inlet gas direction. Can you understand the inlet gas direction? Inlet gas direction from the left hand to right hand. So your SiO2 both substrate actually away from the inlet gas direction. That's why I am loading this alumina board in this direction, because this it will also matter when you will doing the growth. So now I'll place this alumina board in the here at the actually initial end of the stainless steel part or right hand vacuum assembly, and using this rod, loading rod, I'll gently push it inside the quartz tube, and I'll push it towards the desired heating zone, which I have optimized it. Here, I want to mention one interesting note here. What it is, this dimensions, alumina board distance will be different according to your system. How it will be different? Because if your quartz tube dimension is different, then definitely it will be different, because flux will not create same for different tube dimensions. Flux, it means sulfur flux and MOO3 flux. For to deposit the MOS2, we have required both flux in a sufficient amount at the substrate surface. So that's why I'm mentioning here this distance where I'll place the MOO3 sulfur board, where I'll place the MOO3 and where substrate board. So this dimension will vary according to the system. It will not constant for all system. So first we will have to optimize it. Okay, according to our system, and it will also depend on the number of heating zones in your system. If in your system's less number of heating zone, means you can control it properly. If large number of heating zones in our system, so according to that it will vary the distance actually, or insulation between these zones actually, it will also depend on that. Now I'll close the right hand vacuum assembly part properly before loading, before opening the left hand vacuum assembly part. First I'll close it. So it will actually we are trying to eliminate the contamination. So we will not keep it open for a while. So just we have loaded it and we will close it. Yeah. So as you can see, I'm pushing this rod. So may someone have doubt why I am pushing this rod? Because simply, can I close this? Why I am using this rod? So this is actually a heat transfer mechanism is here. When you will understand it, I think it will be a very interesting thing, because using this rod, uh, just I am pushing inside the quartz tube. You can see on the screen, I'm pushing this rod not too much in the quartz tube. At the only the, because my heating zone I started from here. As you can see on the screen, this coil is here for a particular heating zone, but I am pushing this rod only at the boundary edges. So what will do this rod actually, when this quartz tube will heat it, this rod will another end of this rod is directly open it into the atmosphere. So actually it will, as a heat transfer mechanism is here, it will transfer the heat. So what will happen, our right hand vacuum assembly and left hand vacuum assembly will not heat. Otherwise what will happen, during the growth you can't touch it, the left hand and right hand vacuum assembly, if you are not using this rod. So that's why this is the very crucial and very, actually you can say, the cost effective technique to reduce the heating left and right hand vacuum assembly. Because if the in each run left and right hand vacuum assembly will heat, then they will their lifetime will also degrade. So that's why this part is very important. Okay, so this is the heat transfer mechanism. Now I am opening the left hand vacuum assembly to loading the sulfur aluminum. So first I'll take out this heat transfer assembly out, and after that I'll open it. Yeah. So I'll do the same as I have done for the right hand vacuum assembly part, when we have loaded the MO3 coated SiO2 Si substrate and bare SiO2 Si substrate. Yeah. So from this is the actually inlet part of our system. Left hand part is the inlet part, means gases will inlet from here. As you can see on the here is also on the left hand side, these polypyrylene pipe will come from here. Actually, inlet part. This is the inlet part of CBD. Now I load the sulfur board in the quartz tube. Yeah. So in the loading process, I'll do the same as I have loaded for the MO3 coated board. Yeah. Now I'll gently push it into the desired heating zone, which we have already optimized. And we will push it gently and towards the targeted or desired heating zone. Yeah. So this now we have loaded both alumina boards in the quartz tube. As you can see, we have loaded this sulfur boards. I am pointing towards the heating zone number, in which particular heating zone I have placed this sulfur board. But as I have already mentioned this distance between these two alumina boards will vary according to your system. If this quartz tube dimension is different, definitely flux inside the quartz tube will be different for both MO3 and sulfur. So that's why this distance is not same for all system. Yeah, here I'm pointing out towards in which particular heating zone we have placed the another aluminum. Now what we will do, we will close the left hand part, left hand vacuum assembly. So generally one person can do all these things, but if two persons are there, then it is very easy to do. Actually, he can help us. Yeah. So before starting, I think it is required two persons, but when you are operating frequently, so one person can operate all these things. Yeah, now we will push it gently towards the boundary edges. So this is the heat transfer mechanism is also at both ends. So our left and right hand vacuum assembly will not heat it. Yeah. So now what we have done, we have loaded both alumina boards, which consist substrate as well as precursor for the MOS deposition. We have loaded both boards. We will check it again. We have placed in the desired location. Actually, we can say the optimized location, and after that we will close the lid properly. So now we are checking it. Yeah, we have placed in the desired or optimum location. Now we will close the lid properly, because during the process we can't open this lid. So if we have placed these boards in the quartz tube, now we will have to wait for to complete the recipe actually. So first we will check it actually. Yeah, we have loaded both alumina boards on the desired location. Now we will close the lid. So now we will check all other things. Yeah, these lids are closed properly, and all other valves which we have opened, these are closed properly. Otherwise, what will happen when we will open the vacuum pump? This vacuum pump will not work, means vacuum will not create inside the quartz tube. Another thing, what will happen if you are not closing the lid properly, our heating zones will not heat properly. So that's why we are checking again before starting the recipe or before starting the CVD growth process. We will check all these valves. These are closed properly. After that, we will start the recipe. Yeah, now we are opening the MCB to provide the power supply, and we will open the other MCB which are associated with the power unit of CBD, and we will open the CPU to control or monitor the CBD growth. So that program at which particular heating temperature we have provided for desired heating zone, and yet carrier gas flow rate, at what flow rate we have optimized it, we have already mentioned in the one recipe or one program actually. So that program we will run in this system. So yeah, so now we are opening both cylinders. We will have to check it, these cylinders. Yeah, now we are providing the actually carrier gas or assist gas during the recipe run. So now we will open it both the cylinders. yeah. So here, as you can see, I'm pointing out when both cylinders were closed. So it is showing actually the error. What error? It is showing input pressure too low. It means no gas actually inlet inside the system. When we have opened the cylinder, so it is showing input pressure has come back to the normal. It means we can run the recipe. Otherwise, what will happen? It will simply, we will run the recipe, simply powder will evaporate, but no carrier gas is actually there. So deposition will not occur. That's why. So here is for actually a safety purpose, as you can say, because this particular window will actually instruct how much pressure inside the quartz tube. So it will instruct us cylinder has opened at what pressure, cylinder, what the cylinder quartz tube pressure is inside the CVD system. So now we have opened both the cylinder, as I am showing now, pointing out towards the purity of the cylinders. So now the pressure has come back to the normal. Now we can start our recipe, which we have already loaded in the CPU or in this particular system. Yeah. So now it will, so the actually pop up. It will alert us our inlet pressure has come back to normal, and now you can proceed. Yeah, this is very interesting thing or important thing here. As you can see on the screen here in the CBD monitor screen, what you can see? You can see actually the schematic of the system, how this system will work it actually. Here, so I'll start it one by one, or I'll describe in one by one. Here, as you can see, here are 4 MFC are there actually. So these are the 4 MFCs. First, from the bottom of the screen, on the bottom of the screen, as you will find it, there are actually 4 MFC. So first MFC, second, third, and fourth, which will control the flow inside the quartz tube. And these MFCs are for different flow rate. Just like first and second, both for 0 to 1000 SCCM. Third one is for 0 to 100 SCCM, and fourth one is for 0 to 10 SCCM. So if we have required in certain condition for very less flow rate of a particular gas, so we will use it fourth MFC. If we have required moderate flow rate 0 to 100, we will use third MFC. If we have required very high flow rate, like as or for instance for cleaning purpose, so we will use it first and second MFC. Hello. 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 Yeah, sorry for.
Yeah, Chandraman, you can continue. I think some of the participant has accidentally unmuted. So
Okay.
sorry for the interruption. You can continue. Thanks.
Okay. So, so these are the 4 MFC, as I am mentioning it, for different flow rates are associated with the CVD system. And yeah, I'm pointing out towards the MFC. Now, what I'm seeing here is the actually the Prani gauge is there to mention the to measure the pressure inside the quartz tube. So these are the actually inside the quartz tube schematic. When you will you are seeing here on the screen, these are the 12 heating zones. So on the below of these heating zones, they have mentioned the actual temperatures, at what temperatures actually we have given, and at the top of these heating zones mention the temperature, at what temperatures they have obtained actually, or they have achieved. So these are the actually temperature scale is also there. So from this screen we can understand it. Yeah, this much temperature particular heating zone has achieved, and this much is required. So and below of these temperatures, they are mentioning the power, how much power this system is given for a particular heating zone to heat the desired heating zone. So power is also there is given. Okay, so these are these things, and on the top of the screen they have mentioned that the number of zones, zone 1 to up to zone 12 or 11 here. So these are the 12 heating zones they have mentioned it. Okay, and the right hand side, when you will see on the screen, what you will find that there is the actually one is for pump is there, and one for purge valve is there. So when the tube pressure goes to above 100 millibar, as I have already mentioned it, when I have started this lecture, purge valve is a safety valve. So as the tube pressure goes to above 100 millibar, this purge valve will open automatically, which alert us our tube pressure is going to above to normal. So what we will have to do, we will have to open other valves to control the tube pressure, or we will have to turn off the gas inlet in the quartz tube for a safety purpose. So this is the purge valve. It will open automatically, which will control by the solenoid valve. Okay. And another thing is here is the actually vacuum pump. So when this pump will on, it will be green, and what will happen when it will green? So it will suck the air from the quartz tube. So inside the quartz tube, vacuum will create. So how much vacuum will it create? With the help of this pump, we can achieve minus 940 millibar up to minus 940 millibar with the help of this pump. So this much vacuum will created inside the quartz tube. So now these things I have mentioned it. And at the at the left hand corner of this screen on the CBD monitor, you will find it there are actually some number is there, but it is not actually clear. But these are some green part is there. Actually, that indicate that our hardware are working properly, proper or not. So these indicate that now. As I have mentioned that in this system, four MFCs are connected actually. So if four MFCs are connected, so if all four are green, it means all four MFCs are working fine. Okay. So similar here, temperature controller circuit and MFC controller circuit. So these parts, this window is very important when you are using CBD, this type of system, as it is available in our lab. So from the screen, you can understand each and everything about this system, how it will work, and to monitor real-time monitoring. It is very required to understand this flow diagram. Okay, now we will see next actually. Yeah, so I'll go into the recipe part in our system, and as I have already mentioned it, I have loaded the program actually in Python. So we can make it if you have required any other program, or if you want to change any other growth conditions for your recipe, you can change it in, but little bit of Python language knowledge is required, but not too much knowledge is required. Simply if you know little bit, you can edit the program and you can store it here. So here I have stored the program, and we will run this program. Okay, from here simply we will select this particular recipe or code from it here, and we will open it. So as you can see on the screen, these are four programs actually I have stored here for different purpose, for different applications actually. Okay, it's okay. Now I have selected this particular program, and what I'll do, I'll open it. Now this code has opened it actually. As I am scrolling down on the screen, as you can see, this code is written actually in Python language. So this code has opened, which someone may have the query, what consists, or what the parameters, or this program actually consists, what the information in this particular program. This program consists at which MFC, or how many MFC I have used during the recipe, which particular gas I have applied on particular MFC, with which flow rate I have used during the growth process. Okay, and in 12 heating zone, how many heating zones I have used during the recipe process, with how much ramp rate I have used to acquire the desired heating temperature, and for how much time I'm going to give the carrier gas flow rate during the recipe process. So all these informations, step by step, I'll provide it to the system, and according to our provided information, this system will work. So what we will do, simply we will observe it. We will sit there and simply we will observe the flow diagram. Yeah, it is working fine, what we have given the information, and we will simply observe it. As the recipe has completed, we will close the system, and we will open the lid and we will take out our sample. So this program is very important part for designing the particular material, 2D materials actually. So in this particular program, I have given this information here. Now what I am doing, I am showing you how much, if someone may ask, sir, as I have designed a particular program, how we will understand it? It is working fine or not? We will have to run the program? No. Before running the program, maybe we have designed a program or it has certain errors. So before running the program in real time basis or with sulfur and MO3 precursor placement, first what we will do, we will check this program. It is working fine or not. How we will check it? If you have done something programming mistakes in the program, so just you will run it, this program will show some programming error is in the program. It will actually show the pop-up. If it is no programmable error in the program or no programmable error, then this program will show the actually temperature profile, carrier gas flow rate profile, other profile. So as I am showing you, I have run the I have opened the program, and now before running the recipe, I am opening the window one by one at which particular heating zone what temperature will achieve with time and at which flow rate. And in MFC, I'll check it at which flow rate it will I have used and at what time it will maintain it. So these things first we will check it before running the recipe on a real time basis. Okay. Otherwise, what will happen? Our precursor will be wastage. And if we are designing a program and we are running each and every time to checking the program, so our precursor will be wasted. So now I'm checking it. It is working fine or not? So as you can see on the screen, as I have selected zone 7, 8, and 9, because I have mentioned that this is a 12 zone CVD. So it has 12 zones. So as I am selecting 7, 8, and 9 zone, it is showing it. I have used this particular temperature profile for this particular program. As you can see on the screen, on the x-axis, time scale is there. It is in second. On the y-axis, it is the temperature scale is there. Okay. So as you can see, for a certain time, it will reach up to 150 degrees centigrade. After that, it will constant. Okay, it will constant for a certain time. I'll also mention it why I'm doing this, why I have used this type of temperature profile. It is also important to understand when you are doing deposition of a 2D materials. Okay, so this temperature profile will not same for all 2D TMD material depositions. This profile will change according to material. Just like I want to mention here, as I am depositing MOS2, this profile is different as compared to WS2. Okay, so here I have what I have done at 150 degrees centigrade. I have kept constant for a certain time. After that, I have again raised the temperature with a certain ramp rate, and I have reached at 750 degrees centigrade. And after that, it has again constant for a certain time. So that is that time. It has constant at 750 degrees centigrade. Generally, we called as dwell time or growth time. Okay. So after 750 degrees centigrade, we have suddenly dropped it to room temperature, 27 degrees centigrade. So you will find it there is a impulse is there. So it has suddenly dropped to room temperature. So this is the temperature profile we have adopted, we have used during the MOS2 growth. Okay. So now we will check other parameters which we have used during the MOS2 growth. So this is the temperature profile. Okay. Now here is the option to zoom it and zoom it, and other options are there. So we can check it according to that. Okay. Now we will check the flow rate after that. So this is the temperature profile I am showing you with the bigger. Yeah. So now these are the actually flow rate profile. As I'm mentioning it, here we can check it. The first we have checked the temperature profile. After that, we are checking the flow rate profile. So on this particular graph, on the below of this particular graph, you will find that there is the number of channel is also mentioned there. Channel, it means number of MFCs actually. as I have already mentioned it has 4 MFCs. So they have mentioned the channel 1 to channel 4 because it consists 4 MFCs. And they have in the graph they have depicted each MFC by individual color. So as you can see, what flow rate we have used, that will that will depicted by a different color. So we can clearly understand it at which particular MFC we are applying particular flow rate. Okay. So if you can see on the screen, if it is visible to you, as you can see, channel 1, I have given the flow rate from 0 to up to, I think here, as you can see, it is touching the boundary. So we will have to little bit zoom out. Yeah, I'll zoom out. Yeah, now I'll zoom out. Yeah, now you can see on the screen. So I have given the flow rate 0 to 200 degrees, 200 SCCM. It is in SCCM. For MFC. Okay, so I have given the 200 SCCM first, and it will constant for a certain time. After that, I have applied certain flow rate in another MFC. So it is very less, as you can see on the parallel to the x-axis actually. So this flow rate is at 2 SCCM. So these are the actually flow rate profiles. Okay, so these are the different flow rate profiles for a carrier gas. So now I am showing at what flow rate profiles I have used during the growth. Now what I am doing, I am running the recipe. As I have checked the recipe, it is working fine with, and I have again checked it. What is the temperature flow rate, temperature rate profile? What is the carrier gas flow rate profile during the growth? Now what I will do, as I am CO, it has working fine. After that, what I will do, I'll run the recipe, run this code. Now it will instruct us. How it will instruct us? Actually, it will pop up. It will give a particular sound. What the next instruction you will have to do. We have when we design a code. So what we do actually, we insert a pop-up there. So that will remind us, because in many cases, what we do actually, we design the code, but after some time we forget some things, which little bit things. So what we do actually, generally we insert a pop-up during the code. So these actually instruct us what the next thing we will have to do in the growth process. So now it is showing the pop-up. So when if you can see on the screen, or it is visible to you, you will find that it is showing us, please open the butterfly valve. Why it is showing us, please open the butterfly valve? Because as I have mentioned that butterfly valve is directly connected with the vacuum pump. So before running the recipe, or before starting the growth, before heating the temperature zones, first we will have to vacuum the quartz tube. Why we will have to do it? Because if something is there in a vacuum quartz tube, it will not be, we will have to make the atmosphere there, inert atmosphere there. So first what we will do, we will create a high vacuum is there to remove other impurities. Okay, so now we have started the vacuum pump. Now I'm opening the butterfly valve, and I'll acknowledge the pop-up. So it is showing, please open the butterfly valve. Now it has given the second pop-up. Please open the open the desired heating zone temperature. So it will reach up to 300 degrees centigrade. So now it is working fine. Now it is what it is showing. It is showing how much time it will take to reach this, how much time vacuum pump will work, how much time next instruction, after how much time the next instruction will be executed. So it will show in the right hand side of the screen. Okay, so at the left hand side of the screen, as you can see on the screen, it has divided in two parts, left hand and right hand side. In the left hand side, the program is there, which we have actually loaded in the CBD. And another right hand side, it is showing the instructions, what the instruction it has executed, and what the next instruction is required to be executed. Okay, so in the we can check it at the right hand corner, actually right hand corner at the screen. I think it is not visible. It here it will be the time actually. time scale is also recipe time will continuously clock is there. So that indicate the that clock is synchronized with our code. So we can understand it. What will be the next instruction, or how much time, after how much time we will have to acknowledge the next instruction. Okay, so we will wait for that. Okay, now what we are doing, we have opened the vacuum pump and we have opened the butterfly valve. Now as you can see, vacuum pump valve, it as I am pointing out, vacuum pump here in the schematic, it has green, actually means vacuum pump is working, it has working. Okay, now it has started working. So what will happen here at the planning is, what will happen, this it will show the actually pressure inside the cost. Okay, so now as you can see on the screen, it has started to changing. Now all these MFC at this time, as you can see, all these MFCs, no MFC are on. Why we are not opening the MFC? Because we are doing the vacuum process. If you are doing the vacuum process, no gas is required at that time. So that's why no MFC is on at this time. Okay, because we are actually taking out the gas from the quast tube. Okay, so now as we can see, what will be the next instruction? After how much time we will have to close the vacuum pump, and the next instruction we will have to perform that. Yeah, as you can see on the screen, only in the bar diagram, as you can see on the screen, only 3 heating zones: zone 7, zone 8, and zone 9. These are 3 heating zones are only going to heat it. Or how much temperature actually they are going to heat up? For up to 150 degrees centigrade. And other heating zones are not going to heat, because in the code we don't want to heat other heating zone actually. That's why only 3 heating zones are going to heat. So as I am mentioning it, each heating zone temperature, each heating zone is independently controlled. So someone may have query why we are heating 3 heating zone temperature. So because we have placed the MO3 coated SiO2 coated Si substrate board, alumina board, in the 8th heating zone. To maintain the uniformity of the heating temperature, we are heating the adjacent heating zone of zone 8, zone 7, and zone 9. That's why we are heating 3 heating zone here. Okay, I think you have understand it. Now, as you can see, vacuum pump is also continuously working. So that's why this planning gauge is showing the pressure at negative scale, because below the atmospheric pressure. Okay, that's why it is in negative scale. Now, program is working fine, and we will have to wait. So it will instruct us next instruction, or it will give the next pop-up when we will close the vacuum pump. Now, from the recipe window, we can see, or we can check it after how much time we will have to pop up the next instruction. Okay. So here, as you can see, so it has heated up to 150 degrees centigrade, and vacuum pump is continuously on from the as the green light has actually suggested. Now what I am doing, it has popped up. As you can see, it has given the instruction, please close the butterfly valve. When we will close the butterfly valve and we will acknowledge this instruction, so it will close the vacuum pump. Yeah, now we have acknowledged the pop-up, and vacuum pump has closed and MFC has on, as you can see on the screen. Here, as you someone may have queried, here in the after MFC, at the, as you can see my on the cursor, actually on the screen, you will find that there is the on the below of the MFC, they have mentioned that how much SCCM actually I have given, and at the top of that how much it has reached. Okay, after that, one actually square bracket type of there schematic is there, 2 parallel actually connected there, one for certain MFC and the second for flush. Flush, it means what the actually cylinder pressure will directly connect it to the coast tube, that indicate the flush. So here at this time, flush actually at the flush, it is showing the green symbol there. It means actually at gas at what pressure has actually inside the cylinder, it has directly connected to the coast tube. Okay, so we are not controlling with the MFC. Why we are doing this thing? Because for after performing the we have created some vacuum inside the quartz tube. Now what we are doing, we are cleaning it if some other impurities are required. So what we will do, we will simply connect the cylinder with the flash. So what will happen, high carrier gas flow rate profile, high carrier gas flow rate will come outside the quartz tube. So it will remove all other impurities from the quartz tube. That's why we have directly connected the cylinder. As you can see, it is showing the flash is on. Okay. So someone may ask why we are connected as argon gas here. Argon gas. Argon is an inert gas. You can also connect nitrogen gas if it is required. Okay, no problem at all. Now, as you can see, as we have applied the gas inside the quartz tube, it is very genuine. Quartz tube pressure will come down because it has very high vacuum has created. As you will fill the gas inside the quartz tube, so it will comes down to the atmospheric pressure. Okay, so now flash is on, and this is going to change it. Minus 972 come down to room temperature, room at atmospheric pressure. Sorry, 180p. Okay. Now it is going to come down. Okay, as you can see on the screen, it has it was actually minus 940. Now it has reduced up to minus 125. Means it is going to continuously decreasing, as you can see on the screen. Okay, yeah. Now I have opened this manual purge valve. Now on the screen, as you can see, I have opened the manual purge valve. Why I have opened it? If I not opened it, directly cylinder pressure is connected to the quartz tube. What will happen? Our quartz tube pressure is increased up to the 100 millibar. As I have already mentioned that for a safety purpose, as the quartz tube pressure goes up to the 100 millibar, our purge valve will open it. That's why we have opened the manual automatic valve. So this gas will flow using this valve. Okay, so quartz tube pressure will not increase. As you can see on the screen, it has constant now, plus 40. Okay, now it is showing the instruction, yet after 12 minutes MMC flash will be off. So we will wait the next instruction and flash will off. Okay, so these are the actually steps when we you will perform the experiment. So you will have to also do all these things, and I think you will understand in very detail why we are doing these things or why it is required. Okay, so we are trying to give a very experimental aspect for you. So now, as you understand, now you can see flash is off, and at the first MFC, when you will see in the schematic, now flash has closed, and we are giving 200 SCCM certain flow rate with the controlled MFC. Now, as you can see on this thing, okay. So at the pressure bar, as you can see, it has come to 0. Okay, atmospheric pressure. It is 0. It means we are working at atmospheric pressure. Okay, it is showing 0. It means we are working at atmospheric pressure. Now next pop-up, what will be the next pop-up? It is or next event, it is mentioning it. Barrier preparation stage has finished, proceed to the next stage. And at what time will be the next pop-up? It is mentioning it. Okay. Now these three heating zones are heated up to 150 degrees centigrade, as you can see on the screen, and 200 SCCM flow rate is continuously on, and all other pump are off, purge is off, and other instruction means these are the actually barrier preparation stage. Preparation stage, it means before proceeding the recipe, before proceeding the growth, first what we will have to do, we will have to clean the substrate, we will have to clean the quartz tube, we will have to, that's why all these things are just cleaning purpose. To maintain the uniformity, quality of the deposited material, we have to require to do all these things. That's why yes, I have at the beginning of this talk I have mentioned that this process is similar to the food cooking. When we will cook the food, similar, we will cut all the vegetables in a proper manner, clean all these things. So that's the similar process, similar type of process we do. After that, at last, what we will do, we will perform the experiment. Okay. Now recipe time is continuously on, as you can see on the cursor on the monitor. Now next pop-up has come, preparation stage has finished, so we have acknowledged that pop-up window. Okay, now as we have acknowledged the pop-up window, so next instruction was to reduce the MFC flow rate. Now MFC flow rate has reduced, it has come to 10 SCCM. Okay, now MFC flow rate has reduced or it has come to 10 SCCM. Okay, now we will wait to complete this recipe. Now the recipe will work. Okay, so now the temperature is continuously rising from 150 to now it has reached 234. It means it will try to reach up to final value what we have actually given for in this program. What the value we have given in this particular program? 750 degrees centigrade. So it will reach enough what ramp rate we have mentioned in the program. So that rate, with the help of that rate, it will try to achieve that particular final value. Okay. Now please look at on the screen. This program or recipe has completed. Okay, so it will take actually this program or this code actually take complete 1 hour to complete this program. But here I have actually shown the final stage. Otherwise, what will happen? This lecture will not finish in within 2 hours. That's why I have taken. I am showing the final stage. I'm not showing the intermediate actually. Yeah. So now the program has completed, and now as you can see on the screen, temperature has reached up to 750 degrees centigrade. Growth has taken sufficient time or dwell time, what time it has actually required, and it has come back to the normal temperature or room temperature. Now we will open the lid. Before opening the lid, first thing you will have to very carefully, you will have to check it. Our temperature inside the quartz tube temperature has come back to normal, means below 300 degrees centigrade. After that, you will open the lid. Otherwise, it will be dangerous for you. Okay. So now temperature has come back to normal and we will open the lid and we will check it. Now, as you can see on the quartz tube, we have placed the sulfur board. So sulfur board, as you can see on the quartz tube, inside the quartz tube, what you will find that your sulfur board has empty. It means complete sulfur has evaporated, and what you will find that some part of the sulfur has deposited on the left hand part, which is in greenish color actually. Okay, sorry, yellowish color, and some part of the sulfur has deposited on the right hand side. And on the right hand side, you will find another thing. What will be the another thing? Molybdenum, MO. In which color? It will be in blackish color. Okay. So these things indicate that these precursors has evaporated completely, and carrier gas has transformed from one left hand vacuum assembly to right hand vacuum assembly. That's why some part of a sulfur is also available on the right hand side. Okay. So these things indicate that our carrier gas is working fine, and our both precursors are evaporated properly. Okay. And one important thing, or please make one point here. When you are placing sulfur in the alumina board, please keep one thing in our mind. Please take a little higher amount of a sulfur in the sulfur board. Means some part of the sulfur should be left after the recipe in the alumina board. Why I am mentioning it here? Because as it is observed that MOS2 during the MOS2 growth or other sulfur associate 2D materials growth, sulfur conditions should be rich. Why it should be rich? Because when the sulfur conditions should be rich, MOS2 quality should be up to the level. Otherwise, what will happen? If sulfur deficiency is there, it has your monolayer growth has many sulfur vacancies. So quality of the MOS2 growth will not be good. Another thing, another parameter to taking higher amount of a sulfur in the alumina board is that if you are taking a higher amount of a sulfur in the alumina board, so some part of the sulfur will be left in the quartz tube. So you can take assumption from there. Yeah, during the whole growth process, sulfur was sufficient. It means why I am mentioning it here, because sulfur is evaporated at 180 to 250 degrees centigrade. MO3 evaporated at more than 580 degrees centigrade. So if sulfur evaporated first before evaporating the MOO3, then MOS2 will not form. So sulfur will be sufficient during the growth. That's why take a higher amount of sulfur during the growth. And when you will go through the literature, what you will find that they have taken very high amount of sulfur during the growth. That ratio is called as a precursor ratio. Precursor ratio is generally written in sulfur by MO ratio or MO by sulfur ratio. And in that case, you will find that they have taken if 1:4,000 and more than 4,000. So this type of ratio they have taken. That's why this is the reason why they have taken higher amount of sulfur during the growth. Okay. Now, when you will go forward, what we will find that, yeah, little amount of sulfur is there. When you will find a little amount of a sulfur, but someone may ask, in the alumina board, there is a reddish color part of there actually. So when the sulfur is evaporated or sulfur melt, it changes its color. When you will load it, it will in yellowish color, but when it will melt it, it will in yellowish, reddish color. That's why. So liquid sulfur is there actually, not solid sulfur. Okay, understand? Yeah. So now we have this part of CVD. Now on the both hand side of the cost tube, as you can see, precursor had deposited. It means it clearly indicates that precursors has evaporated properly and our process has completed. And on the screen, it is showing recipe has completed. Now what we will do, we will dislodge the both alumina boards and our substrate. Okay, we will do the same as we have done for the loading purpose. Okay, now we can check it. All MFC are closed. All heating zones temperature has come to the normal, and we will dislodge the samples with the same process we have done for the loading purpose. Okay, so we will first what we will do, we will open the SEM. You can open the left and right vacuum assembly, any. But first, what we are doing, actually, we are taking the substrate first. Okay, so that's why we have opened the right hand vacuum assembly. Now, with the push pull rod, we will take out the gently. We will have to. This step is also gently. What will happen if your rod will stuck with the cost tube? Then it may be the possibility cost tube has damaged. So please keep this point in our mind also when you are dislodging the sample or alumina boards. Now we will dislodge the alumina boards and we will take out the sample on it. Okay, and we will keep it. We will keep it in plastic box. Please don't keep it in directly plastic box. What will happen, because substrate has it is heated actually. So if you will place it directly in the plastic box, it may be actually melt. So that's why please take some tissue paper or something on the bottom of the plastic box. After that, please place the substrate there. Okay. Now we will close the right hand and left hand vacuum assembly properly. We will not keep the open for a while, because humidity will come out into the chamber and it will not good for the deposition purpose. Now we will close the lid also. Otherwise, what will happen? Some means maybe the possibility of damage. So this is the complete demonstration of a MOS2 via CVD, monolayer MOS2 deposition via CVD. Okay, so this is the complete demonstration part of a CVD. So now some only the transfer process, because we have deposited MOS2 on SiO2 Si coated substrate, and now we have required to transfer it on different substrate actually. So what we do, we have used the bed transfer process. Okay, all these steps we have done in our laboratory with the in the guidance of Dr. Shaibal Mukherjee. Okay, so these steps we have performed in our laboratory. Now, what we will do, we will transfer it monolayer MOS2 by using bed transfer method. So now, as you can see, MOS2 generally when you will do the optical analysis, or you will perform a SAM actually surface morphological analysis or surface morphological experiment, AFM also, SAM also, and optical also. What you will find that MOS2 is in triangular form. Generally, it is observed. So this is an MOS2 on silicon. This is the optical image actually. Okay. Now what we will do, if we have required this MOS2 on different substrate, so what we will do, we will try to actually lift off this MOS2 monolayer from SiO to Si substrate to different substrate. Why we are transferring on different substrate? Someone may have the query, because MOS2 is not visible from the neck dies. If it is not visible from the neck dies, so that's why I am showing you the optical images. Okay. If it is not visible from the neck dies, so to make the contact on the top of the layer, it is not easy. Okay. So what we do actually, first we will make a contact on a particular substrate and we will transfer it MOS2 on that device. So that will be I think easy. So that's why we are using the transfer process. Okay. So now what we will do, we have deposited MOS2 on this substrate and we will do the coating. Particular polymer, we will coat it here on the top of that. So, and I have already explained the spin coating process before, so I'll not mention it in here. Okay. Now we will coat the polymer layer coating. What will we do the polymer layer here? Polymer layer actually will assist the transfer of MOS2 layer from this substrate to the target substrate. Okay. So now we will coat the polymer layer on top of the MOS2 layer. Okay. So now we are putting the polymer layer on top of the MOS2. So adhesion between polymer and MOS2 should be sufficiently high. If adhesion between MOS2 and polymer layer is sufficiently high and adhesion between MOS2 and substrate surface should be very less, then the MOS2 layer will be lifted off from the substrate. If this criteria or condition is not fulfilled, then that case MOS2 will not lift off. Okay. So many polymers have suggested by researchers or renowned authors in this field. So we have used one polymer for this purpose. And what we will do, we have deposited the polymer layer on top of the MOS2. We will kept it at 85 degrees centigrade for 15 to 20 minutes in a hot air oven. Okay. And that process is called baking actually. Okay. After waiting for 15 minutes, we will take out the sample and we will actually remove the edges. We will remove the polymer layer from the edges of the deposited substrate. Okay. Why we are doing this? Because to penetrate the DI water between the MOS2 and substrate surface. Otherwise, what will happen? Water will not penetrate. This process is called as actually surface energy assisted process. Why this process is called surface energy assisted process? Because MOS2 is in hydrophilic nature and SiO2Si is in hydrophobic nature. It means both surfaces has different nature for DI water or water. That's why water will penetrate between them. Okay. So with the help of this technique, we will try to lift up the MOS2 layer from the substrate. Okay. So we have removed the edges of the. Now what we are doing, we have placed the PDMS on top of the polymer layer. Why we have placed the PDMS on top of the polymer? Because PDMS will also assist or help to handle the MOS2 layer. Because MOS2 layer is very thin. It is 0.68 nanometer. It is a thickness of monolayer MOS2. Okay. So it is a single atomic thick actually. Okay. Now what we will do, we have placed the PDMS. And what we will do, now we will take the sample which consists PDMS, polymer, MOS2, and we will dip it into the DI water. Okay. So what will happen? DI water will penetrate between MOS2 and SiO2 Si substrate. So now we are dipping, we will dip it continuously or repetitively. So what will happen? Water will penetrate. Okay. From where water will penetrate? From the edges where we have removed the polymer layer actually. Okay. Now we will try to lift off with the help of PDMS that layer and MOS2 layer actually. Okay. So now as you can see, only the substrate SiO2 Si substrate will be left, which is blue in color actually. Okay. Now the layer has come in the PDMS and we will transfer it into the glass substrate. for a experiment, for a demonstration purpose. Okay, and now we have transferred the MOS2 layer. But not only MOS2, here the polymer is also there. So now what we will do first, we will do the reverse process now. What we will do first, we have deposited the polymer. After that, we have done the PDMS. So first, we will reverse it. We will remove the PDMS first. After that, we will etch the polymer. Only the MOS2 will be left on the substrate surface, on the target substrate surface. So we will heat up to 50 to 60 degrees centigrade. So in the hot plate, so now the PDMS has removed and only the polymer, as you can see, I'm pointing out the arrow. So only the polymer and MOS2 layer is also only there. So now what I will do, I'll dip into the toluene solution. So polymer layer will be removed. Now I'm dipping it into the toluene solution, okay, to remove the polymer. So this solution will not affect the MOS2 quality and MOS2. It will not affect the anyway the MOS2 actually. Now MOS2 has transferred. As you can see the optical image after transfer process. Complete MOS2 from the SiO2 Si substrate on glass has transferred. So this is called as a PET transfer method of MOS2. Okay. So this particular deposition process, transfer process of MOS2 has covered till now in this lecture. Now only what part of left? Only the sensing part is left. Okay. So these are the actually sensing setup in our lab. So different type of gases with different concentration is available, and these are the sensing setup in our lab. And these are the source meter, heater is there, DMM is there, and system is connected with the source meter. Okay, to measure the real-time monitoring actually, and hot air oven is also there beside of the system. Now this type of contact or electrodes be used to actually measure the sensing performance of any material. So we have also transferred the MOS2 on these electrodes. Okay. But here I am showing you another, before using this device to evaluate the sensing performance of any material, first we check it is okay for evaluating the sensing performance or not. How we will evaluate it? We will check it if it is showing the open resistance, open or high resistance, it means any electrode is not short or it is working fine at the contact pad. Okay. So first we will check the device where it is working fine or not. So now we are checking the device with the help of DMM, or as you can see on the clearly. Now this resistance is for heater actually, because on the below of the contacts heater is also there. Okay, to heat the particular temperature of material. So this resistance comes from heater coil actually. Heater is also there. Okay. So this resistance for heater and overflow for electrodes we are using it. Okay. So before using the device for any material, otherwise what will happen if we will not do this analysis? If we will not do this, what will happen? Current will flow from this metal part, not will flow from our material, and we have required the performance of our material. So first we will check it. Our device are working fine or not. After that we transfer the material on this device. Okay. And after that we evaluate the sensing performance at different realistic conditions, such as different humidity conditions, different temperature, and other different ppm concentration, different selectivity, all these things, other parameters we consider here. Okay. So now I'm depositing hydrothermal deposited MOS2 here. I'm not depositing in the MOS2 because transfer process of MOS2 I have already mentioned it for monolayer. Now I am dropping the hydrothermal actually MOS2, which I have fabricated with the help of hydrothermal actually. Okay. So now as you can see, now I am covering the electrodes part actually. Okay. Now I have, so this electrode part I have covered it. Contact part is left, as you can see on the screen. Okay. So this is a contact part is left. Now we will heat it for to remove the humidity and other part from the material. So we will keep it for 24 hours, and after that we will take out from it here and we will place it into the chamber. Okay. So I'm making a contact here. So this is a actually heating chamber, sensing chamber. So I'm making the contact on the device to evaluate. Now, as you can see on the screen, deposited material is also deposited there. Now we will close the chamber, and as you can see on the screen, this is the actually base resistance. Base resistance it means material resistance when no gas is exposed on the material surface. When we are able, when we are checking the device, it is showing the overflow. But after depositing the material, it is showing some resistance. It means, which clearly indicate that this resistance is for material, which is the base resistance for the material, without any gas exposure or any other temperature condition or humidity, without any conditions at room temperature. Actually, this resistance. Now we will close the chamber properly, because we are now what we are going to do. We are applying the different gases at different flow rate, different concentration. So these are the MFCs. Very precise MFCs are connected in our circuit to actually to expose the gas on the sensing surface. And we will open the different gases. We will apply the gases and on the device, and we will evaluate the sensing performance of our device. Okay. So now as you can see on the MFC, now we have applied it NO2 here 101, and it is coming into the chamber. So this is the complete actually sensing setup and sensing part of our deposited material. So I think so I have demonstrated all these things from deposition to the sensing performance of our deposited material. Now, if you have any queries related to this, please ask. Thank you very much. Now I'm.
Now, floor is open for the questions. Participants, you can ask questions directly to the speaker. Are there any questions from the participants?
Sir?
Yeah.
Sir, this sensing parameters, I think it will depend on the surface area.
Surface area, not. Okay, so your question is sensing performance will depend only on the surface area. This is your
yes,
question,
sir.
or anything else? Okay.
Sir, what are the mechanisms?
Okay,
that,
for sensing purpose.
Plays main role for the sensing parameters.
Okay, for sensing parameter, actually sensing depend on the many parameters, not only the surface area. Yeah, I agree with you. Surface area is one of the factor for sensing performance, but not only one surface area. Because if you have a different types of material, okay, so different type of materials, it means particular material is suitable for particular gas sensing. Understand it? Just like I want to mention you, if I am using a single metal oxide, which is suitable for NO2 sensing, if I am doping it with palladium or noble metals, platinum, other metals doping, what it will be selective sensitive for H2S. So this type of sensitivity actually sensing performance changes according to the selection of material also. So we can't say ki only the surface area will play a role. Many things are there. Selection of materials are also there. your surface morphology is also there, your composition. If you are making a organic and inorganic composition, as Dr. Shaibal in the morning session has explained in a good way. So that's why it not only depend on the surface area parameter. Okay.
Okay, sir.
Any other question? If there are no further questions from the participants, then
Sir,
we
one
can
more question.
okay.
Yeah.
Hello.
Sir,
Yeah. I want to clear my thought that you have shown that yellowish color in the left side of the CVD, and black is that dependent on the density of particular gas, particular material, or why this yellow is in the left side, or
okay.
black
Okay. When you will take the sulfur powder as a precursor, it is also in yellow color actually. Okay, first thing, that's why yellowish color is there. And
so it's before reaction it deposited on the CVD.
Sorry, can you repeat?
It means it deposited on the CVD before reaction.
No, not before reaction. No. It will not deposit on CVD. When we will take the sulfur powder in the alumina boat, it is also in yellowish color, because to fabricate the MOS2 or to deposit the MOS2, we will have to take the precursor. So we take the sulfur powder in a certain amount, as I have shown in this lecture. We have taken the 200 mg sulfur in the alumina boat, which we kept in the actually left hand side. So that is also in yellowish color. Okay. So yeah, sulfur powder, how much sulfur powder is deposited on the left hand side, it definitely depends how much powder you are taking in the alumina boat. If you are taking higher amount of a sulfur, then more sulfur will deposit it on the left and right hand side. Okay.
Okay, sir.
And as you have asked the color, so I want to mention here one point is here. If a sometimes what happen, molybdenum oxysulfide is also there. That will be in white color actually. So if someone is interested or someone is doing the deposition and you find that there are three colors, green colors, black and white type of color. So please don't confuse. I think that may be the molybdenum oxysulfide. Okay, not MOS2. Okay.
Okay, sir.
There are no questions. Let's then, we are switching. So I request all the participants please follow and fill the feedback form by the
Sir, your voice is not clear, sir. Please repeat.
Sumit, your voice is not clear. Can you repeat?
I'm just saying, please fill the feedback form which we will share by the end of the day and given tomorrow.
Thank you, participants, for joining for today's session. I think Sumit might be having some issue with his voice, with his audio connection. So thank you for the joining us today. Please meet us again tomorrow morning, and we'll be shortly sharing a feedback form with you all. So please feel that it will be very beneficial for our work. Thank you.